the slides up. Okay, good morning from Texas, Austin, Central Time Zone, and welcome to ORC's first tentative venture back into the world of physical meetings. So this is our first hybrid meeting, so we're doing a few things differently this time. For those of you who don't know me, I'm Keith Mitchell, ORC President. Before we start the workshop proper, I'd just like to run you through a few logistical things for the workshop, and then for those of you who are new to ORC, a little bit of background about the organization and also a couple of member updates. So, as I said, it's a hybrid event. We have a conduct policy to make sure that everybody has a good experience, and that applies online as well as in person. When you signed up for the workshop or as an ORC member, you agreed to be bound by that. Everybody generally behaves very well at ORC meetings, so please ask you to note and respect that. The workshop is being recorded. As usual, it will be available on our YouTube channel a few weeks after the event. Also, this time around, it's just to make everyone aware that we may have one or more members of the press present, which was great to get the attention. Very welcome. We're not having audio participation from remote participants. The only people that you will see speaking are people who are physically in the room here, or our speakers or session chairs. The event time zone is Central Standard Time, which is UTC -6. So just be aware of that when you're looking at the running order. We're present all using social media platforms. Hashtags we're using are LoveDNS and ORC37 this time round. Now, most of you will be very familiar from the use of the Mattermost chat platform for remote participation in our workshops over the past year and a half. Because we're running a hybrid meeting, we're stepping up the use of that this time. So we'll be using it for Q&A and talk rating, which we previously did via Zoom, which obviously doesn't work for people who are physically in the room. So they will be doing that via Mattermost. Everyone will be doing that via Mattermost. So if you're not already signed up for Mattermost, please do so if you want to interact. And there will be general discussion there as well. And Mattermost is you can sign up at our site. And there's clients or web browsers, both work equally well. There's a Q&A section at the end of each talk, 5 to 10 minutes, depending on the length of the talk. Now, the way we're asking the questions is you use the workshops channel on the Mattermost chat, but if you tag it with the hashtag question, then Ray Bellis, who is one of the board members who has kindly volunteered to be our Q&A monitor today, he will see that and he will read your question out. If you're physically in the room, we have a microphone. I don't think any of you need to step more than about 3 meters to get to the microphone. But again, Ray is watching that, and that will give you a chance to actually speak. It will be first come, first served, time permitting, and obviously please identify yourself and your affiliation when you're asking the question, whether you're doing so in person or remotely. For polling, we'll be doing Mattermost. I'll be driving that during the Q&A section at the end of each talk. You will see a poll pop up, and you can respond minus, negative, neutral to that. And with that gives the PC and the speakers very valuable feedback on the process. And there's also a general event survey, which we'd appreciate you filling in, because it's asking you some questions about what we can do to make you feel more comfortable to participate in person. We were hoping for better than 10% participation in person, but it's good to see everybody. And also some questions about where we put our next workshop. So that's the introductory stuff as far as the workshop is concerned. If you've got any questions, you can also ask in the workshops channel, and we'll do our best to help out. So just briefly, some introductory information as far as ORC is concerned. If this is your first workshop, welcome. It's great to see you here. And a little bit of background on ORC, and also a few member updates as well before we start the meeting content proper. Okay, just waiting for my slides. while we're doing that, for the people in the room physically, just to brief you, should you hear a fire alarm, it is not a drill this morning. And if you need to exit, then don't use the exit at the back of the room. Pick either of the doors at the side of the room. You will find that there is doors to the stairwell open, and you should proceed to the lobby in the event of any emergency. Okay, so yes, a few brief introductory remarks. What is our work here for? We're here to make the internet's DNS work better. And there's a bunch of different ways in which we do that. We're very strong on facilitating participation between researchers and operators through data sharing, through coordination. We do a bunch of useful tools and services, open source software, and also various platforms that we operate for collaboration. And it's about responsible, confidential information sharing, transferring knowledge, and also doing a little bit to make the world aware that the DNS is there. And you know, it isn't always the DNS's fault when the internet breaks, for example. We have a very diverse community of members, over 100. Our member base has been extremely supportive and stable through all the challenges of the pandemic. I'm pleased, however, to say that we've had a few new supporters and blue members join recently. And also you'll see the fresh growth in the middle of the tree as Cloudflare have signed up as a gold member, which is great to have them on board. What have we achieved? What did we get managing it last year? We did a bunch of funded software development. We got a very good amount of funding there. The DOH enhancements to the DNS performance tool were funded by Comcast and Wisiol. Aaron funded our PKI root origin validation to our Check Me DNS tester, and we've also recently completed adding public suffix data sorting to our domain statistics collector. That was funded by Nick.at. So we very much appreciate that. It was a good year for grants. We did 3.5 online workshops last year. We also did very well financially. We exceeded 1 million revenue for the first time. And we've also built up our cash to the point where we effectively have a year of operating reserves in place. The DANE Life, the Internet data collection took place in 2021, and we've started work on doing that for 2022. And there was significant progress in cleaning up our systems and automation in general. If you want to become an award member, there's various categories. The 2 entry-level categories have some conditions attached to them. You know, if you're interested in joining or upgrading your membership, then our membership coordinator, Steve Sullivan, will be very happy to help you. We attempt within the work to have industry best quality governance. We're an independent, neutral organization. We are, as I say, diverse membership and financially self-supporting. We're various committees that are used from the member base. And we're in the US, we're recognized as a nonprofit 501c3. Who are our board? We have 1 board member here, Ray. The rest of the board are joined online. Ray and Joao were elected to the board in the October 2021 AGM. And Paul, Jacques, Benno, and Jeremy have all been serving on the board for some time. Org staff, myself and Dinesh are here. The rest of the team are present online. So if you need help with systems or software, talk to Matt or Jerry. Steve joined us in the middle of last year as our new membership coordinator. I think Steve's been doing a great job of reaching out to you, but he's there if you need help with anything. And we also have another team member, Pam, in California. And we're looking for more people. We really need another systems engineer. We also have vacancies for a software engineer and administrative help. So if you're interested or you know somebody who's interested, you can find out more about these positions on our career page. Program committee. The program committee does an awesome job of putting our content together for these workshops, and they did it again. There's very high quality of submissions. We even have some content which we'll probably save for the next workshop potentially. I'd like to, we appointed Pallavi as our new program committee chair. And I'd like to welcome Hazel, John, and Suzanne as our new program committee members. So that's the background about the organization. There's plenty more information if you'd like to know more. if you're an ORC member, you get to do some other things. I have a few updates for the ORC members. We're not doing because we have a shorter workshop today. We're not doing an ORC member only section. But Benno, the board chair, also chairs the privacy committee and asked me to share with you an update on where the privacy committee is at. We formed the privacy committee to basically address the fact that our participation and data sharing agreement are now somewhat old, and we need to address the tension between meeting the requirements of modern privacy legislation such as GDPR and CCPA, but balancing that with having less restrictive policies on use of our data set, which are proving a bit cumbersome. So since ORC 36, which was relatively recent at the end of November, the Privacy Committee has nailed down its charter for what it's working on and has conducted a survey of how our members and supporters use their data. The Privacy Committee is continuing to work on these. They will be writing up the results of the survey in a report. And based on the charter, they're drafting a plan and actionable items to move things forward. And that includes some questions that will require professional legal input in terms of the current agreement, and input from policy and privacy experts will be solicited. And the Privacy Committee will also be seeking to engage with the members to get your views and input on that. The other thing that we're soliciting member input on is our tool set. We have a very large tool set now. A lot of development on this has either been incremental or it has been externally funded. What Jerry would like to do is for some period of time focus on a particular aspect of our tool set and do some major development of that. You know, it could consist of refactoring some code that's been accreting for a while, or major addition of new features and functionalities. And if there's going to be a focus, it needs to be in one area of our tool set, not just across the board. So there's specific input solicited in terms of should we focus on the testing tools like DNS, perf, DNS, JIT, and check my DNS, or should we focus on the statistical measurement tools like DSC, DSC data tool, and DNS-Cap? We did a survey, we got 30 responses. It would have been nice to get more responses, but I mean, additional input is still welcome. Jerry has written up the results of that summary and we'll be circulating that on Monday. So if you're interested in this, you have a view, please read that as a NORT member, and then we'll be scheduling an online discussion in the middle of March to have a interactive discussion with the members on how we should take that forward. One of the other things that we did over the past few months was that Jerry ran what we call crash courses on making use of DSC and Grafana. These were kind of informal learning exercises that were quite well received and pretty good participation in these. So Steve Sullivan would run something similar for how to use the ORC member portal. You know, it's not exciting software, but it is an important part of your ORC member experience. It makes your life easier and our life easier if you're fluent in this. So Steve will be doing short sessions to help you with that, giving you some tips, answering your questions. Obviously we can add features to it as well. And we're trying to make things more automated and smoother workflow. So it would be good to have member engagement on that as well. So if you're not a member, that's just a glimpse of some of the things that you get as a member. You get to have input into how we develop our tools. You get input into how we develop our policies and manage our data set. You get input into how to make use of the features and services that we provide to you. There's a bunch of other reasons to become an ORC member if you're not already. You know, this is the community of the experts that are running the DNS. So it's a great place to learn and engage and interact. We've had a few operational incidents over the past few months where it really felt to me like because people were able to connect on ORC, it made a difference and it caused these issues to be resolved more quickly. It makes me proud as a team and a community when we do that. Provide various resources, and we're also a trusted neutral party. We're not here to boost our shareholder value. We're here to make the internet's DNS work better. That's pretty much all I had to say. I mean, I'm in the words of our members, hear how sad the value that some of our members experience. So please consider that, or talk to Steve or one of the team if you're interested. Anyway, that's all my non-technical content for the day. I will now hand you over to the reason you actually came here, which is to listen to the talks and learn stuff. For today's first session, we'll impart from the program committee as a session chair, and Ray is our Ray Bellis from the org board is our Q&A monitor, and that's it from me for now.
Thank you, Keith. And also on behalf of the program committee, a warm welcome to Org 37. I think we have assembled a very interesting and stimulating program. Starting with our first speaker, I'm very happy to present to you Siva Kakarla from the University of California, Los Angeles. Welcome back, Siva. Siva will present finding bugs in your DNS zone files before deployment with GRoot.
Hello everyone, I am Siva, a final year PhD student at UCLA. Today I'm going to talk about how you can find bugs in your zone files before deploying them with the help of our tool GRoot. This is a collaboration work with Ryan and Behnaz from Microsoft with my advisors Todd and George at UCLA. And this work got published in SIGCOMM 2020 and also won the Best Student Paper Award then. It is well known that DNS misconfigurations lead to service disruptions. So I'm going to talk about a specific DNS outage that originally got us interested in the DNS space. One of the worst outages due to DNS is the one that happened at Microsoft in 2019. On May 2nd, almost all of Microsoft services became unavailable for 20 hours. And this included Azure, the cloud computing, Xbox Live, Office 365 Dynamics, and more. So what happened here? Well, the problem started when connectivity to Azure storage services was lost. Subsequently, services that depend on storage, basically anything running on a VM, so almost everything, started to fail, and these services also became unreachable. This whole thing lasted for almost 20 hours. And after debugging the problem, ultimately, the engineers found that the problem was due to a one-line manual change to a DNS zone file during a routine migration. So just a minor misconfiguration caused such a havoc. This incident and other such incidents highlight two key takeaways about why DNS misconfigurations are often disastrous. The first was that DNS is inherently global in nature. If you can't look up the IP address for a service, then you lose connectivity worldwide. So DNS has a very unfortunate property of what we call having a large blast radius. The second was that resolving DNS outages is extremely tricky. Remember that the Azure outage took 20 hours. And the primary reason is that DNS relies heavily on caching responses to queries, including negative caching. This means that when storage became unreachable, everybody cached that fact, making it hard to restore connectivity. A user generally thinks DNS is a simple system. You send it queries, you get back queries. However, it is a very different view from that of an organization that is managing the zone files. DNS is significantly more complex than people realize. It is essentially a complex, very complex rewriting system. There are two sources for this complexity. The first is that there is non-determinism in the DNS. The resolver can choose any one of the available name servers to resolve the query, which can lead to different answers. The second is the record types and the certain interactions among them. There are different kinds of rewrite records, alias records, wildcard records, and about 60 other kinds of records defined across about 30 RFCs. To put it concisely, I would quote Jeff, who said that DNS is a lot like chess. It's a simple game in terms of the rules, but phenomenally complex in the way it can be played. Now let's talk from an organization point of view. What are some of the properties that the organizations and the DNS operator want to ensure about their zone files? UCLA DNS team might want to ensure that UCLA.edu always resolves to this IP address using the UCLA zone files. Other teams might want all their queries written the same answer regardless of non-determinism. Or their query should not be rewritten at any point in the resolution. Before I talk about how we verify these properties, let me give a brief overview of how operators ensure them today. There are two main approaches. One is to do testing or monitoring. So you make a change, then you run some queries, or you actually monitor for connectivity. There are two big problems with this approach. This is not proactive, so you'll only find bugs that have already impacted the actual network. And this is not exhaustive. You might test some queries, but the question is, have you tested them all? And it is not obvious how to test all relevant queries due to the complexity of DNS. The second approach is to do manual review of changes using best developer practices. However, humans make mistakes, as we have seen earlier. In contrast, what we have done is built a tool called GRoot that will do proactive and exhaustive verification of the correctness of DNS zone files. GRoot takes in a set of zone files, possibly from many different name servers. It also takes a specification of what the zone file should be doing. This includes user-defined properties like the ones I showed earlier. Given these two inputs, it either ensures that these properties are satisfied or it gives counterexamples. The important thing to note here is that there are way too many queries to enumerate naively. A domain name is a string made of characters with about 30 different values, and a domain name can be up to 254 characters long. Plus, there are 60 different record types. So there are clearly way too many queries to enumerate and test. The way that we solve this challenge and the key idea in GRoot is to first partition all the queries into query equivalence classes using the zone files. An equivalence class is a set of queries that have the same DNS resolution. GRoot then evaluates the behavior of many queries at the same time by picking one query from each equivalence class. GRoot generates small number of equivalence classes, providing a massive reduction in complexity. We also have good results so far using the tool. We have run it on 3 different organization zone files, a large cloud provider, large campus network, and a large CDN provider. One challenge was that we did not have a specification in the sense what the IP address should be. So instead, we focused on finding behaviors that should basically always be wrong, like loops, delegation inconsistencies, black holes, and so on. In the cloud network, we found 4 cyclic zone dependencies and in many cases of delegation inconsistencies. In the CDN zone files, GRoot revealed around thousands of black holing issues. A rewrite black hole is a case where the query is rewritten at least once and then it does not resolve to any IP address. CDN had many such issues due to incomplete decommissioning of host names that are no longer in use. And after GRoot, they initiated a cleanup of their zone files. Let us take a closer look at the university results. The zone files in the university are managed in a decentralized fashion, with departments managing their own zone files. We obtained the campus zone file and 895 subdomain zone files using zone transfer. There were in total 120K records with 4,200 CNAME records and 63 wildcards. And it only took 7 seconds for GRoot to check this to check and verify these zone files. The result after checking properties through GRoot are as follows. The functional violations in the first table are considered bugs, while the properties in the second table showcase GRoot's ability to help operators explore and understand the behavior of the DNS of their DNS zone files. Violations of the properties in the second table are not necessarily bugs, but are interesting behaviors that an operator may be interested to examine. There were NS records mismatched between parent and child zone files, and some of the NS records pointed to a web server instead of a DNS name server. These bugs affect the visibility and redundancy of the zone and also increase the query response time. When asked, the operator said that to check if a name server is working properly, they directly use the IP address instead of the name, so they never caught these issues. In another case, we found CNAME loops where the CNAME was rewriting to itself. When asked, the operator said in a straightforward manner that the reason is just negligence and they were not checking the zone files properly. Finally, we also found 48 cases of rewrite black holing, which is an NX domain after at least one rewrite. It happened in multiple departments in the campus. So one of the operators said it was due to CNAME entries missed during prior retirement. And another operator said they were mostly entries orphaned accidentally when the source server was removed a few years back. Operators can use GRoot to explore properties like the one shown in table to understand their zone files better. One of the checks was to identify lookups that use an external name server That is a name server that is not under campus.edu. Most of these name servers not in the campus belong to AWS or Cloudflare and are likely intentional. But one name server was x.campus.ed, which looks suspicious. And when asked, the admin said it's a typo, and thanks for the information about delegation, we have corrected it. To be clear again, GRoot guarantees that out of all the possible queries, there are only 24 cases identified under campus.edu that are rewritten more than twice. Now, let us look at how GRoot works internally with the help of an example. What I am showing on the slide is the example files for 5 zones spread across 3 name servers. There are D names, C names, wildcards, and wildcard C names in this example. First, GRoot parses the zone files and builds a data structure called a label graph, which you can think of as roughly representing the union of all the records in the zone files, plus the addition of special alpha nodes that represent an arbitrary sequence of characters. We add an alpha node child to every node in the tree. Finally, we add other edges for DNAME rewrites in the graph. For instance, since there is a DNAME rewrite from mybanker.com to banker.com, we add a director edge between these nodes, shown in the purple on the slide. Once we construct this label graph, we proved several theorems about this data structure. Basically, the idea is that every path from the root in this graph to any node is an equivalence class of queries. Each equivalence class is a compact representation for a possibly large set of queries. In particular, we prove that all user queries corresponding to a path will have the same DNS resolution behavior, the soundness. So every query in an equivalence class will have the same behavior. And we also prove that every possible query belongs to exactly one equivalence class, the completeness. So we cover all the queries. These theorems means that if we validate the behavior of each equivalence class, then we have exhaustively checked the correctness of the DNS for these zones. Here I have shown one such path from the root. Each type is its own equivalence class, but GRoot executes the uses for all record types at once using a compact bitset representation for types, splitting nodes when different types experience different behaviors. So now let's take a look at this equivalence class and see what happens. Given this schematic query, we then execute or simulate the DNS semantics on this query. The way we did this is that we formalize the execution of DNS mathematically from the RFCs. That is how it should execute. I'll skip the exact details here, but show an example of that, how we use this formal model. Here is the example equivalence class from before, and now I'm going to show its execution. We start with the root name server, and the query is alpha.mybanker.com. Because the answer is a name server referral, we now explore both the possibilities. First, let's go to ns1.fni.com and we repeat the query of the name server. From here, the execution rewrites alpha.mybanker.com to alpha.banker.com using DNAME record, and then the execution splits based on the query type. For an A record, we get an answer at this name server for the IP address, and for the other types, we get an empty answer. The execution then will continue for the other name server. A key insight we had here was that by pre-dividing the equivalence classes in this way, the execution of the DNS never needs to directly inspect the value of alpha, so we can leave it opaque. Next, we check properties on these graphs. Consider a simple property like answer consistency, which means that the user should receive a single response irrespective of the server he contacted. That property is represented as a graph property that different sync nodes must return the same answer. In this graph, we notice that different sync nodes return different responses, so there is no answer consistency. And the other property is rewrite blackholing. There are no rewrite blackholing in this graph, so that property is satisfied by this equivalence class. Rewrite blackholing is basically a path from the root to a leaf where there is a rewrite and then followed by an instrument. There is no such thing happening in this graph, so that property is satisfied by this equivalence class. We have an implementation of our tool GRoot publicly available on GitHub. It is written in C++ and it's quite fast. To test GRoot performance, we created zone files from the publicly available DNS census records. DNS census has zone files available publicly in the CSV format. And there are around like 1.3 million second level domains like co.uk. And in total, there were 65 million records, and of which 3.4 are CNAME records and 218 DNAME records. We ran GRoot on each of the 1.3 million second level TLDs, and the results are shown in this graph. GRoot can scale linearly to tens of millions of records, so it is pretty fast compared to the size of the zone files that we have. To conclude, GRoot is our tool for verification of DNS zone files, and it is proactive and exhaustive. We also developed and use a formal model of DNS for GRoot verification. GRoot provides all queries that violate a property. And we have some good results so far. For example, the university, we found like 109 bugs. And we submitted to SIGCOMM, and it won the Best Student Paper Award in 2020. And it is available on GitHub, and I can be reached at this email address. I have another tool called Ferret that uses GRoot's formal model to check RFC compliance bugs in DNS namespace implementations like DINE, not PowerDNS, and others, and found many bugs. I also gave a talk at OR 35 about this, and is also on GitHub along with the dataset. Please check that out also. Thank you.
Thank you, Siva. So I think I hand it over to Ray now to handle the questions and answers.
Thank you, Willem. Okay, we're starting with two questions from Peter Thomason. The first is, how can GRoot check that responses by all named servers are consistent? If it only looks at the zone files, it doesn't know about the servers.
It assumes that it can check the responses based on the current zone files. And if it cannot, then it just says like, I cannot verify. If there is, let's say, a name server where a query is being sent to some other name server and you don't have those zone files, then the graph does not build more and then stops there. And GRoot reports that, okay, we don't have access to that data, so I can't verify whether this sequence class is satisfied or not.
Okay, thank you. And the second question also from Peter Thomason. It appears to me that the error conditions that were identified, missing glue, loops, etc., can be identified directly by looking at records as is without investigating the full query space with equivalence classes. Can you name an example that can only be identified by grouping into equivalence classes?
I would say like all queries should not have some property, like let's say all queries should not be written more than twice, or there should not be more than 2 hops for any query resolution under all my subdomains, then you definitely need GRoot.
Right, thank you. Okay, and then from Josh Kyo, how well does GRoot handle configuration above and beyond resource records? For example, if I have 3 DNS views and view A forwards to view B, causing a forwarding loop, is that something that GRoot can identify?
I am not sure if I am aware of folding, but if there is any kind of loop in the resolution, then definitely GRoot will identify it.
Okay, thank you. And then from Peter De Vries, why did you choose the name GRoot since there was already a GRoot in the DNS realm?
I don't know, like we came up with that. Like we wanted something that rhymes with root, so we said root, but root is too common, so we said GRoot.
Yeah, I mean, yeah, personal comment from me. Yes, as you already noticed, probably found this confusing myself. I mean, I work for FRoot. We have GRoot and GRoot. It's a little odd. Okay, and now from Nils, any plans to provide a Python API?
Unfortunately, no. Like I don't have anything on mind, but if they're willing, then I can provide. If somebody is willing to use GRoot, then I'm definitely happy to provide a Python API.
Okay.
Currently, the input is taken in the format of like a JSON. So you can give the zone files and then mention the properties that you want to check on the zone files using a JSON file, but I can change it to a Python API also if it's.
Okay, I think that was all of the questions because they've been coming up while I've been reading them out. So I think, yes, that seems to be all. Thank you very much, Siva. And
yeah, thank you, Siva. Yeah, it's very nice that you have, I see on your slide, indeed, at org 35, you were working on fixing name server software. And this time it's fixing the DNS zones. So I'm wondering what will be fixed in DNS by you next time. So very happy to have you. Thank you again for your time. So our first speaker in the second session is Daniel Dubnikov from Tel Aviv University. And Daniel will be speaking about improving the performance of DNSSEC in his talk, especially the non-existence things, I think, in his talk called Adaptive DNSSEC. So welcome, Daniel. Happy to have you here.
Okay, so my name is Daniel Dubnikov. I'm a graduate student in Tel Aviv University. And today I will be talking to you about recent research work I've done together with my two supervisors. We call it Adaptive DNSSEC. Of course, this was a joint work together with Professor Yuda Afek from Tel Aviv University and Professor Anat Brenner-Bar from the Reichman University. Both are my supervisors for my thesis work in Tel Aviv. And this work couldn't have been done without the great support of the Againt project and the Blavatnik Cyber Research Center in Tel Aviv University. Okay, so right off the bat, so what did we try to do? So first of all, we wanted to test how big of an impact you get when you move from using plain DNS as an authoritative name server to one of the two most common flavors of DNSSEC, NSEC and NSEC3. Then we wanted to test that over a stream of NX domain attacks. And the numbers you see here are how many queries per second the overall system can sustain when they start losing packets. So when they reach, let's say, 23,524 queries per second on average, with plain DNS, we detect that packets are starting to be lost and the system can't handle these kinds of stream of NX domain attacks. And with DNSSEC, the impact is significant. We get the performance which is less than 50% of the baseline that plain DNS gave us, and it can be a problem. So now let's go a bit deeper to what exactly did we test and how we tested it. So we tested NX domain attack, which probably most of you already know. So let's do this quickly. DNS relies heavily on its caching, and when everybody behaves, the caching can be used very good. And this means that very quickly resolvers get to know everything they need to know about some sort of an authoritative web server. Let's say it's Sony here in this example, and they respond from the cache, and Sony doesn't have to participate and have to do the extra overheads of communicating with that authoritative web server. But when malicious entities get into the picture, they can just surpass the caching very easily. They use random names that do not exist in the cache and will never be queried again. And for each of these names, they have to query the authoritative name server to know if that name exists. And of course, it doesn't exist. So there's a lot of extra communication. If you have an army of bots, let's say, then you can use that attack to take down an authoritative name server. But this has happened in the past, and I suspect will continue happening in the future, at least in the recent future. So this one we wanted to test. We wanted to test the system under this NX domain attack when the cache is basically useless. And how did we do that? We did that with a simple experiment where we had an attacker that runs those NX domain queries, and we have an authoritative name server that either uses plain DNS or one of the DNSSEC flavors, and then the validating resolver. The validating resolver validates the responses from DNS if they are in DNSSEC. And what do the results tell us? The results tell us is that if you're an authoritative name server and you're using plain DNS and you want to use the benefits of DNSSEC, you want the integrity, you want the authenticity, and then you basically are open to DDoS amplification. And in the eyes of an attacker, they would prefer to attack you as an authoritative name server if you use DNSSEC as opposed to if you use plain DNS, because they would need less power to attack you compared to if you had plain DNS. This we can clearly see from the numbers. So let's dig a little deeper. What does it mean to say that something doesn't exist in DNSSEC? So let's see it with an example. Let's say you're querying the name DDD of name.com, and you want to know if it exists, or the authoritative uses DNSSEC. And so it will respond with an NSEC record saying that everything between ABC and LMN lexicographically doesn't exist. So what happened here? You asked about DDD and you get an answer that has nothing to do with the DDD itself. It just tells you that there is a big range of infinitely many names that do not exist. And DDD happens to lie in between, so it also doesn't exist. And as you may notice, this gives you a lot of information, much more information than just what you queried. You queried about DDD, and now we know infinitely many names that do not exist. Can you use that? And the answer is yes, there is an RFC for that, and you can use that and to synthesize NX responses. So as a resolver, now with, let's say, you already have that record cached and the TTL hasn't expired, and now you're being queried for another name, it's the BBB, that no one ever queried you before. You don't have to communicate with the authoritative server. You can use the cache and say that it doesn't exist. And what if the attacker tries to get something that is outside this range? Then you get another record with another range, another infinitely many names. And very quickly, you will have all the names in the zone, and you will know exactly which ones exist and which one doesn't exist, and you just can answer from the cache when you're under these sorts of attack. What does it do to the performance? Well, it's amazing. So if you have a baseline of 23,000 queries per second with plain DNS, and you got a serious hit when you move to DNSSEC, now if aggressive caching is in the picture, then you actually get a boost. You're actually performing much better than plain DNS, like 3 times or more better than plain DNS. And this is because the caching is used better than plain DNS. Even if plain DNS, you still can't use the cache when somebody attacks you with NX responses, but with DNSSEC, you actually can use the cache for every type of query. And there's a little caveat here that we only tested it under node because we couldn't get that feature enabled in bind and unbound. But what do we lose? What are the problems? So there are 2 main problems with using DNSSEC with NSEC or NSEC3, and that's the main reason is what we call zone locking or zone enumeration. And as you've seen before, I said that very quickly you get an idea of all the names that are in the zone. So you can very quickly, when someone uses DNSSEC, have an idea of all the names that there is in its zone. And it can be a problem, not for all of us, but for some, let's say, I don't know, NSA or the Pentagon, and you really don't want people to know all the names because it's a security hazard, then you have a problem when you use these NSEC or NSEC3 implementations. And there's also a scalability issue that we saw in many large DNS providers that they documented it in their blogs, that it's a problem for them because now there's no one-to-one correspondence between an NSEC record and the name that doesn't exist. When you get a new name that doesn't exist, to find this specific NSEC record, it's not as simple as just querying for something in the database. You have to use some sort of a more complex data structure, like let's say a tree. Okay, so what can you do? How can we stop zone locking? So the short answer is you basically can't unless you use online signing, unless you sign something online with an asymmetric encryption. This was proved with by Goldberg et al. In their NSEC 5 paper. And the implementations that we know today that do use online signing in order to prevent zone locking are black lies, white lies, and NSEC 5. How do they do that? They do that by generally all of them use a similar idea, which is when you are getting query for a name that doesn't exist, let's say nxname.com, then you create on the fly a new NSEC record, and the NSEC record has a very small range, maybe 0 length range, that says everything between nxname.com and nxname.com, or some epsilon doesn't exist. So you as, let's say, an attacker, you don't get any new information about anything other than NX domain doesn't exist. And the bad thing is that you have to sign this NSEC record because everything in DNSSEC has to be authenticated in order to not be forged. So all of these new records that we create on the fly, we need to also sign them with asymmetric encryption on the fly. And what does it do to the performance? Well, we take another hit. First, we got a big hit when we dropped from 23 to less than 10K. Now we get an additional hit, and with white lies and black lies, you're getting 30% or even less. And this is really bad because, as we said, some entities just have to use these options. They can't use the basic NSEC or NSEC because of the zone locking, because of the scalability issue. So for them, what we're going from plain DNS to, let's say, black lies, they will have to give away 70% of the throughput of the system. So we also made a little schema that shows what exactly is happening here. We want to use DNSSEC because DNSSEC gives us the authenticity, but then we have an increased packet size and additional CPU loads. So we really want to use aggressive caching. Not everyone implements that, and even if they do, it might open the door for zone locking or scalability issues. So we now have to use white lines and black lines to solve these problems. But now we're back again into the problem of the increased packet size and the added CPU load, and we're in some sort of a cycle. So how do we break out of the cycle? So this is where we propose a new solution. And the idea of the solution is, let's remove the overheads. The two overheads we have are the packet size, where we have to add additional things to the packets or additional packets with the signatures. And the signatures can be really big if you want to use RSA, for example, with a lot of encryption. And also added CPU load. Okay, you have to validate as a validating resolver every record that you get back from the authoritative DNS server. And if you use online signing, now as an authoritative server, you also have to use asymmetric encryption to encrypt the records. So these are the overheads. How do we get rid of them? Let's not do that. Let's do them once and forget about them. How can we do that? Let's say we use TLS. TLS is an encrypted connection where we authenticate once as an authoritative DNS server, let's say with the key of the DNS chain. And now every communication on that TLS connection, as long as it's open, is considered authenticated. So we don't have to now send the signatures with the DNS. We can just use plain DNS over the TLS connection. So this is the basic idea. And how can we sustain the TLS connection forever? We can't. We have to close it eventually. So we want to decide when to use TLS connection, when to use simple UDP over DNSSEC. So the idea is to use a hybrid solution. When the traffic is high, let's say we're under an attack, then we opt to upgrade our connection from plain DNS, from UDP to the secure TLS with plain DNS. And when the traffic goes back to being low, then we can go back to using DNSSEC over UDP in whichever flavor works for us. And exactly how we decide when to use high traffic, when to use low traffic, I will go into this in a bit. So we wanted to test this, wanted to go over and the numbers and see the throughput of the system with our solution. So we set up to do a POC, and we had some bumps in the road. The first one was, how do we implement that inside the already implemented bind, unbound, node, whatever the DNS clients that are available and popular today. It's not a very easy task, even if it's on open source. So instead of doing that, we decided to do it with proxies. So proxies give additional overheads, but it's okay. And what we do is basically have one proxy in the resolver machine, one proxy in the authoritative machine. And instead of the resolver and the authoritative speaking to each other, they speak to the proxies inside their individual machines. And the communication between the machines is being done by the proxies. And all of our new logic is being implemented into the proxies, which are independent from the bind and unbound implementations. And there we can decide when to use the high traffic and when to use the low traffic. What is the second problem we had? The second problem we had was with the TLS. So we ended up seeing the TLS has overheads that are a bit high, and also it suffers from what is called head of line blocking. In short, it means that between a resolver and authoritative DNS server, we will open a lot of communications during an NX domain attack, because we have to query a lot of names that do not exist, and every one of those names would use a single TLS connection with virtual connections within it. And if one packet is being lost, and there's a high probability that this will happen when the traffic is really high, then all the communication has to stop it to retransmit that packet. This is what the head of the line blocking is. And how do we solve that? We don't use TLS, we use Quick instead. Quick is a relatively new protocol. It's a relatively new, it was, I think, designed in 2012 or 2013, so almost 10 years ago, but now it's being implemented more and more. It was designed by Google and exactly to solve these problems, and it uses UDP instead of TLS, instead of TCP, excuse me. And how does it solve the head of the line blocking? Well, it uses UDP, so now it has some sort of virtual connections implemented into it. And when a packet is lost for one specific connection, you don't have to stop all the communication, because it doesn't go over TCP, it goes over UDP. You can stop only the communication for that specific stream, and all of the rest of the streams can still go, work with UDP. So this is how we solve the head of the line blocking. The second thing that the Quick has that gives a lot of benefit is 0-1 round trip time, which means we can basically resume a connection with zero overheads. And the last thing, which is very important, is that we don't use TCP. We use UDP, So we don't have to worry about firewalls or IPSs that will block any DNS communication that's not over UDP, because we actually are using UDP.
Daniel,
yes.
You have 5 minutes until your Q&A time.
Okay. I'm close to the end. So how do we tear down and start the quick connections? Okay, so let's not do that. Let's keep them alive as long as possible. The overheads of having quick connections long live is very low, and we can even turn down the connection and keep some things in the memory and resume it very quickly. But what if we really have to close connection because we have resource limits, there's no infinite memory, and then we score the connections using an exponential moving average, where we basically give each connection a score, and the higher the score, it means we get more packets more recently. The lower the score, we get less. And so we use some sort of an LRU, and when we really have to close the connection, we close that connection that has the lowest score. This is how we do that. Okay, so we're all set to run the experiment. So let's do a quick recap. The quick recap is that we, as the baseline, had 23,000 queries per second for the plain DNS. And when we moved to NSEC and NSEC 3, we took a hit of more than 50%. And then when we really had to use white lies, black lies, or NSEC 5, the performance dropped to less than 30%. And so we're really hoping that our solution would be as close as possible to plain DNS. And we were super excited when we saw that the solution we came up with, we call ADADOC, which means adaptive DNS over quick, performs with 20,000 queries per second, which is only 13% less than the plain DNS, very close to plain DNS, which is really exciting for us because this was only a POC, and we can make it even better in the future. So what are the conclusions? The conclusions are that if you opt to use the DNSSEC over DNS because you want to gain the performance, you are actually susceptible to DDoS amplification, as we've seen with NX domain attacks. And if you use our solution that we call the adaptive DNS over quick, get a hybrid solution where we're using light and fast connections over quick. We only do the asymmetric heavy encryption once, so the overheads are low when an NX domain attack is happening. You get a throughput that is very close to plain DNS, which is what we aimed for, and you don't have to compromise your security. You're not susceptible to zone walking, and you don't have the scalability issues just because you can use black lies or white lies that don't have these issues for the low traffic, and when you're moving to the high traffic, then you're just using plain DNS, so there's no issues here. So that's it. Ended up in time. Questions?
So the first two questions coming from Hazel. The first is, how does this differ from regular authoritative DOT? What is it that is novel here?
Well, first, the novelty is that there's a hybrid solution, right? Because with authoritative or DNS over TLS, then you would have to open a connection for each incoming request, right? At least for like 2 minutes, and then you have to close the connection, and then you have to open one again. So here we have a better system where we keep the connection up for more time. The second thing is, of course, using quick, which was not yet proposed, which I think is better than using plain TLS.
Okay, thank you. And then a follow-up also from Hazel. I would also be interested to know whether the proxying architecture proposed here is actually a necessary part of this improvement.
No, it's not necessary. It's something that we had to do because we didn't want to waste too much time trying to implement stuff inside an already huge projects of bind and unbound. And we wanted to do something that would perform as close as possible, but will be implemented more quickly.
Thank you. And then from Ulrich Visser, how does NSEC 3 enable zone walking? Dictionary attacks are doable on plain DNS, so that is not an argument.
Well, if you look on the research, there's many ways to get almost all the names in the zone, even if you're using NSEC 3, because you can use dictionary attacks, because you have offline, you can offline download all the NSEC records and you know how they were encrypted, right? And then you can just go over with, I don't know, some high-speed graphics card or whatever that can do these SHA-256 and try a lot of combinations until you find something that works. This would be the name. So it's not 100%, but it can get very close to it, okay, even with NSEC3.
Okay, now from Petr Spacek. Have you estimated performance impact of resource exhausting attacks on the TNS quick level as opposed to DNS level? Say an attacker intentionally overloading the server with repeated handshakes without resumption.
Yes, so we didn't check that. This is still something that we need to verify. But we suspect that even in the worst case, it will perform as bad as running black lines. It won't be worse than that, because then you will have to do the encryption every time, and it will be the same as having to do that for like in black lines.
Okay, thank you. And now from Evan Hunt, you said you were not sending the signatures over the TLS connection. This implies the clients can't do local DNSSEC validation.
So for the clients, it should be similar to, so first of all, the clients can trust the resolver, they usually do. And if they don't, and they have to do that, then you can extend the idea to the communication between the resolver and the client, because they're using they're using also an encrypted communication, let's say DNS over TLS, right? So you can extend the idea for that as well.
Thank you. And next from Ralph Weber. How do you think to get resolvers and authoritative to work together technically and commercially?
Yeah, that's a big thing. Yeah, in DNS everything enhances really slowly. So I'm not sure how, but if you give them enough of an incentive, if it can get them a return on their expenses, then maybe it can happen. Okay,
and V. Kunat, I think this is Vladimir Kunat. I'm a little confused that to improve performance of DNSSEC, you ditch it for transport security. Redoing crypto sounded like you were limiting yourself to online signing.
Yeah, you basically do online signing only once when you establish the connection, and then the communication uses the symmetric encryption, right? And everything on it is considered authenticated, like using HTTPS. You only use the asymmetric encryption once, and everything that you get after that, you say, okay, I now know it has to be the server. So you don't have to do the encryption over and over again, the asymmetric encryption.
And now Paul M. I'm sorry, we've only got a couple of minutes left now, if that. Was there a difference in the degradation of performance of DNSSEC when elliptic curve algorithms were used instead of RSA in the signatures?
Yes. We didn't go into that in this talk, but there is a big difference, especially when you use the online signing algorithms, because then you have to sign records with elliptic curve cryptography, which is worse, and it performs worse than RSA.
Okay, and with apologies to the couple of questions that we won't have time for, maybe you can take those questions on the list afterwards or on the channel. The last question is, why would an attacker honor your request to switch to the faster channel?
Okay, so if the attacker is not a resolver, then it doesn't matter. If the attacker is a resolver, then it doesn't have to do that, right? You can just not do that. But if it doesn't do that, then you can either, as an authoritative, reject that resolver and it won't be able to serve its customers, or you can just accept that and don't use that. And if that happens, then you go back to being with the performance of DNSSEC without the benefits.
Okay, thank you, Daniel. So yeah, there are a couple of questions we've not had time for, so maybe if you can address those in the workshop channel, thank you. And sure. Back to Willem. Thank you.
Yes, thank you, Daniel. Indeed, it was a very stimulating talk, raising a lot of questions with the audience, so thank you for that. So our second speaker in this second session will be Nils Wisiol from the Technical University of Berlin and from DSEC. And Nils will present on an actual implementation of a quantum-resistant DNSSEC algorithm in his presentation, Post-Quantum DNSSEC Falcon Signatures in PowerDNS.
Yes,
Thanks.
thank you.
Start.
Hi, my name is Nils Wisiol, and I'm a PhD student at Technical University of Berlin. And today I'm presenting a little project that I did with Mathieu and Peter together. And we implemented the Falcon 512 signature scheme in PowerDNS to use it in a post-quantum secure DNSSEC. So why would we do that? Shor's algorithm, I'm sure you've heard of it, breaks all signature schemes that are used in DNSSEC. Well, given a quantum computer that is sufficiently large, that is supposedly available within the next decade. So given the speed at which things change in the DNS, we should start worrying about this now. And maybe you're asking yourself, why don't we just use DOH or DOT? Well, those provide transport security, and that is different from what we're trying to achieve with DNSSEC. So in DNSSEC, we need to have integrity all the way from the zone owner to the resolver, and that is not achieved by DOH or DOT. When we want to integrate a new signature scheme in DNSSEC, we need to look out for a couple of things. The first is we need fast validation because the resolver is going to validate a lot of signatures in short time. We also need short signatures because the DNS has restrictions on the packet size, at least for the UDP transport. So to make things convenient, we want the signatures as short as possible. And also we want shortish public keys for the same reason, actually, as for the signatures, just the keys are transmitted not as often. So here we can afford some more time if it has to be that way. So why did we choose Falcon 512? Well, that's mostly because of research done by Moritz and others. They checked all the NIST candidates that are available for signature schemes, and they determined that Falcon 512 is the best candidate in terms of well, the requirements that I just mentioned. The security of Falcon 512 is roughly equivalent to 256-bit ECDSA, and it's a bit stronger than RSA with 2048 bits. And when we started the project, no other post-quantum DNSSEC implementation was available, and that's why we thought we wanted to fill this gap. Okay, so what is the mission of this? We wanted to create a real-world experimental setup where you can see and how the post-quantum DNSSEC could behave in the real world. So we want to see how is the key storage working on the authoritative name server. We wanted to see how is the performance for key generation, signing a zone, and the validation on the resolver. And we also wanted to see, is this compatible with existing DNSSEC infrastructure or existing DNS infrastructure? And one most important thing to consider here is the packet size. So yeah, how did we get Falcon 512 in PowerDNS? Well, we didn't implement Falcon 512 ourselves. Instead, we swapped out the OpenSSL library that PowerDNS can use and switched it for a OpenSSL fork that is maintained by the Open Quantum Safe project, and they actually implemented Falcon 512 in that library. And all we had to do is fork their fork to add another high-level API that makes things very convenient to access from PowerDNS. So we added this EVP interface, and then added also a crypto key engine class for PowerDNS to use the Falcon 512 implementation of the OpenSSL fork. And basically, that's already it. It was not very hard to add to PowerDNS. And I wanted to thank Mathieu again for doing all the heavy lifting on this work. So once things compiled, basically, the first thing we looked at was the database storage requirements, and we know that the secret key of the Falcon 512 scheme has 1281 bytes, and the public key has 897 bytes. And because of base 64 and formatting overhead, what ended up in the database of PowerDNS was about 3 kilobytes per key pair. If you compare this to other key sizes that we observed, it's a lot, especially if you compare to ECDSA and Edward Curves algorithms. On the other hand, if you compare to the usual RSA key size, it's still more, but I think it can be handled. So this shouldn't be a showstopper. Yes, so much for the key sizes. Now let's look at the performance. And the first thing we did was we ran the performance test that PowerDNS ships. And this just, when you call this command, PowerDNS tests all the algorithms it knows, also in different libraries it may have available, and returns the performance for a mean of 100 samples. And what we did is we ran that many times on my laptop, and yeah, and then we draw the results. So for creating a new key pair, what you can see here is in red, you see RSA in different flavors. And although there are different signature schemes within DNSSEC, they're all using the same key size, which is 2048 bits, and only different hash functions. And because the RSA operation is the expensive part here and not the hash function, they appear to use the exact same time. In green, you can see the ECDSA much faster than RSA. And in blue, you see the Edward curves. And then finally on the bottom, you see Falcon. And you can see Falcon is actually, in creating a key pair, it's a bit faster than RSA, but slower than the other options. For signing, you can also see that Falcon is a bit slower than, well, actually a lot slower than ECDSA, but also still faster than the RSA option, which, you know, it was doable in the past. And finally, for verification, you can see that Falcon is actually faster than all other options except for RSA with 2048 bits. So overall, this doesn't look too bad, but we wanted to also confirm the Falcon performance in like a, let's say, more real world setup, not just in the test bench that was shipped with PowerDNS. So what we did was we created a sort of mini setup with a authoritative server that signs zones below .example. And we added a validating PowerDNS recursor. And we connected those two with a Docker network. So this is all running on the same host. And the Docker network, we use it for UDP connections only. This is also for very large packet sizes that I talk about it later. And that's just because we want to measure the validation performance. We don't want to measure time performance drop caused by TCP fallback. And then we add a test client, and the test client talks to the validating resolver, and those two are actually using TCP only. So the recursor has a classical trust root for the .example top level domain. And what I mean by a classical trust root is just the ECDSA trust root. The recursor is configured in a way that it will, each time when we send a query, it will actually validate the signatures on the response. So there's no caching for the signatures that we obtain through the response. And yeah, with the setup in place, we just, you know, we send many queries for different for zones configured with different signature schemes, and we measure how long it takes until we get a response. If you're interested in this whole setup, you can find it on GitHub. So this is those are the results, and they're actually very similar to the results that we obtained with the PowerDNS test benching tool. You can see Falcon a bit slower than RSA, but faster than the others. And the important difference from this performance measurement to the performance measurement that I showed before is just the time scale is very different. Here we are on the order of milliseconds, where the previous one was on the order of microseconds, and that makes sense because here we include all the networking overhead. And also the difference between Falcon and RSA has almost vanished because it was very small before, and now it's all eaten up by the network overhead. All right. So I think in terms of performance, it also doesn't look too bad. Now let's look at the packet size, because that may be a problem. So the first thing we looked at was just, okay, we query, you know, 2 IPv4 addresses, or we query, so we get a response with just 1 IPv6 address. And you can see the packets that we receive, again, on the bottom, you see Falcon. They're much larger than what we're used to using RSA or ECDSA or even network curves. But while this looks okay, everything else that we tested doesn't look too good. So I guess most importantly is the DNS key that we have here, the third from below, which is actually required to do the whole validation, right? If the resolver is to validate the response, it needs the key, and the key needs to be signed. So you could say this is already a problem. Also, when you have proofs for non-existent, the response length, the packet also exceeds the magical threshold that would probably be at somewhere between 1200 and 1500 byte. And that makes the packets that are being transmitted prone to TCP fallback, and that may cause problems in the resolution process. I should mention that the packet sizes, of course, vary slightly with the involved query names, but because most of those are well beyond the limit, I don't think the query name can actually make a big difference here. So the packet sizes are a bit concerning. All right, we wanted to create a real-world setup, right? So yeah, why don't you try it yourself? Here we can actually try our example domain at the Google Resolver, and we just asked to see the signatures. And yeah, if you do that on your laptop right now, you will get this answer. And of course, it won't be authenticated data because, well, we just used number 17 as the algorithm number for Falcon, and how would anyone know that we're doing this? But if you ask our validating resolver, then of course, you can see the authenticated data bit, because our resolver understands number 17 is actually Falcon 512 and understands the signature content. And well, if you don't have DIC, you know, conveniently ready, you can also just visit our website and play around over there. Okay, so let's conclude the talk. We tested the storage that PowerDNS requires to use Falcon 512 in DNSSEC. And it's larger than 2048-bit RSA, but I think it's acceptable. And also it could be smaller if you really, you know, put effort in it. The performance for key creation is faster than comparable RSA, but slower than other options. For signing, it's also faster than comparable RSA, and it's slower, unfortunately, than ECDSA. And I guess most importantly, for verification, it's a bit slower than RSA, but not really. And it's faster than the others even. Now, for compatibility, we have seen some problems. The packet sizes are prone for TCP fallback, but we should do some future work here. And also, I should mention that if you're using DOT or DOH, you don't have a strict length limitation for the responses. So that it does not provide the security that we want. That's why we need to use a post-quantum secure signature scheme, but it may save us with the trouble that we have because of the exceeding signature length. Right. So let's look at what we want to do with this in the future. First of all, the question is, I guess, how many validating resolvers actually do not support TCP? So if you're doing this in the real world, how many people would end up having problems resolving your domain name? Is it because of TCP fallback, or is it other problems with, you know, unknown algorithm number, or, you know, what kind of problems could show up if you're actually trying to implement this? Then if it's not Falcon 512, what else could it be? The paper that I mentioned earlier by Moritz and others, they didn't look at Bliss because it's not part of the NIST competition, but for the security level that Falcon 512 provides, Bliss has similar key and signature size. So that doesn't really make sense. But if you want to increase the security level to a higher standard, maybe you're required by law or something, then Bliss could be an alternative because the key sizes don't go up as steep as they would do for Falcon. So maybe Bliss is an option for higher security. Or maybe a hash-based signature scheme that was proposed using a Merkle tree, although I'm not very familiar with the details here, but I think that is certainly interesting to look at. And then finally, if you want to have post-quantum security in the DNS, well, you also need to make the root post-quantum secure, otherwise the whole process won't be of any use, right? So what would it take to make the root post-quantum secure? Well, you need a root algorithm rollover, and while that will be needed someday, the key rollover that we have seen was also already quite a project. So I imagine there's all sorts of issues coming up if you actually want to change the root algorithm. All right, and then finally, I want to mention Jason Gertsen, who also implemented independently of us Falcon 512 in bind. And I'm really curious to see if our two implementations can actually work together. All right, that's it. I'm happy to take any questions.
Thank you, Nils.
Thank you,
Really
Nils.
nice to see implementation of this follow-up of this work of Moritz. Really nice. Ray.
Yeah, thank you, Willem. So Nils, first question here from Jeff Houston. What are the anticipated range of packet sizes for DNS key responses when there are 2 or possibly 3 keys in the response?
Yeah, so for each key, you need to add 900 bytes. Here, right now we already exceed 1600 byte. So if you add another DNS key, another Falcon key, that is, you need to add 900 byte.
Okay, thank you. And from Paul Hoffman, I think you mentioned some of these, but will you also do this for all of the other NIST finalists?
Yeah, if there's demand for this, we certainly consider doing that, because I think the infrastructure is already in place, so it will be less effort than last time, so to speak.
Okay, oh no, we've got a new one. Do you intend in the near future to publish an RFC to update the IANA registry to include an algorithm number for Falcon 512?
Well, I think we first need to figure out compatibility issues and then see if it makes sense to actually do this.
Okay, thank you. Okay, I don't see any more questions, so thank you very much, Nils. I'm back to Willem.
Thanks. Thank you, Nils. I noticed you already claimed algorithm number 17.
Yeah, I mean, that was just, I didn't want to claim it. I just didn't want to use the private or what other reserved area, because I wanted to see how it behaves in the real world.
Yeah. I recently also noticed don't seem to be experimental algorithm numbers.
Yeah, I just didn't want to get special treatment. That's why.
Okay, thank you. So our third speaker before the big break is Erwin Hoffman from the Frankfurt University of Applied Sciences. And Erwin looked into DANE for SMTP and will present on it with this talk. Internet survey of DANE TSLA DNS records, application and use for mail exchanger. Welkom Erwin.
My name is Erwin Hoffman, and I'm assistant professor at the Frankfurt University of Applied Sciences, dealing mainly with network issues and IT security. And one of my favorites also is to support a little bit the software which has been raised by Daniel Bernstein, in particular, or what he has issued back in 1998, something like that, QMail, which I did a refork, which is called SQMail, and also the DJB DNS implementation I have enhanced to support IPv6, the protocol, and also supporting DNS curve right now, which is now included as on both sides in the DNS cache and in the tiny DNS. And also I supply the environment and the community over here with the missing features essentially. So that's partially it's a playground for my students as well. And also, as I said, it's addressing the public. So starting here, introducing a DNS lookup scheme for TLSA records in the email client of SQMail, which is called QMail Remote. I simply was curious to see how is the deployment of TLSA records in the wild, let's say, yeah. And in order to do so, I raised a bachelor thesis. And from the bachelor thesis, we took some zone data, and this was used as an input here for our analysis here. So I have to say, in this case, we had simply to look for the extent how many TLSA records are deployed in the DNS, in particular for mail exchanger services on port 25 only. Yeah. And we are interested to see what are the usage modes in the current situation here. What are the other constraints regarding the other information in the TLSA records mentioned to be selector and matching type, and how they're realized in the TLSA records. And also one of the other research questions was, how do people handle here X500 key rollovers for the certificates and the availability here? And also look for other operational conditions for DANE records here. However, not taking into account to look for DNSSEC records here. That means you do a plain TLSA lookup without considering DNSSEC in the first place, because the implementation I have done so far does not support DNSSEC on the resolver side. So, however, if you have a resolver here now which is able to do some kind of DNSSEC validation, it would be almost the same, since we get the same answers here. And also out of scope was that we check in addition for the X509 certificates we have received so far, since we do not do a real SMTP or ESMTP session, but rather simply do a DNS lookup here so far. So what we did was to grab from the zonefiles.io a couple of websites, TLDs, which we did analyze so far. Unfortunately, it took out that these information data were not complete at the time we took it. It was done in September last year. However, we took now the GTLDs, which are info, org, and net to some extent, and also some European sites, which we believed are quite interesting, because we thought it's quite much likely that those domains have a sort of TLS coverage here, TLSA coverage here, and also some American Asia Pacific sites we used here. So that's what we have had as an input. So what is our method essentially? We did actually let's say a two-tier lookup for the TLSA records. The first lookup was to check whether a certain domain has an MX record available. That means the first step was to look for MX records and IP records, of course, here. So it turned actually out that a lot of those responses we have received essentially are not very well described. So we received a lot of localhost stuff. And also we figured out that we have a lot of MX services now received pointing to google.com or hotmail.com or even outlook.com. And we did not consider those in the further analysis so far. For each domain now, we simply emulated the behavior of a standard email client. Usually an email client, if it does not receive some kind of DNS responses, it does a retrial once more, or third time or fourth time. I call this here a a quadratic DNS lookup in time, and in order to compensate for the situation that the authoritative emails DNS server actually does not return with a valid information so far. And this set includes now some 66 million domain names, which we have been looking for so far, and receiving for and now taking the MX data we have received. We did on those basis some kind of TLS lookups in addition so far. As I said, DNSSEC was not required here. And the cache we are using, that's the DNS cache out of that suite, did not essentially do an iterative query on the authoritative name servers for the respective zone, and simply looking for the answers over there. This could result in some kind of UDP or TCP DNS responses, of course, and also what we have heard in the previous talk. The buffer sizes on the receiving side is quite important in here, and in my implementation I have chosen a packet size which is valid here to be of 1228 byte, which is a little bit below the MTU size for IPv6 networks so far. EDNS0 responses were accepted as well. Now let's have a look here at that picture. What we have here. Essentially, we can see what is our main setup. The main setup is essentially a caching server, which does a major work, and we use the client on the very same server here to formulate the MX query and gather the MX data for the particular domains. And in a second step, actually, we took the valid MX answers and did do a TLSA lookup so far. So this actually emulates what we have usually in a standard SMTP dialog in order to receive a valid data from the name server and to compare the received fingerprint of the certificate with the then essentially received X509 certificate in the SMTP dialog as well. So what we actually had here is we send about 300 million DNS queries in total, essentially, and this actually corresponds to some kind of 1 gigabyte of data, which are available on the GitHub. I'll give the link later on in my presentation here so far. That's the essential idea.
Erwin,
so
you have 5 minutes until Q&A time.
Yeah, okay, fine. So what we received so far was a very peculiar kind of information. At first, we have to see that the coverage of MX records is not that large than we did anticipate here. What we receive essentially is here what we see here in that slide is the number of domains we have queried here. They are sorted here in the list of the domains in that particular TLD, and in the other colors we see essentially the total MX what we have received and the unique MX. It turned out that a lot of MX records essentially point to this very same server here, so the amount of MX servers is quite small, and the average the given numbers are seen here. So we have 66 domains coming in. We have about 38 million records received as MX records, and about 9 million essentially unique MX names only, essentially. That means we see a lot of MX delegation in the internet here. So in the second step, essentially we did analyze the responses regarding our query for TLSA records, and then things become very slim, essentially. That means we have a lot of MX records which simply are not covered by TLSA records so far. The only domain which is a little bit outstanding is the Netherlands domain here, which have quite some substantial coverage here. So we believed essentially in the first place that those responses are different among the different TLDs, but there is really little information we can see here. So in this slide here, we see the same picture here, but now the amount of TLSA records is enhanced by a factor of 10. So that's the reason why we have that strong number here for the Netherlands domain. So it's really not significant, the coverage of TLSA records regarding MX. So further then, we did an analysis on the information we have received in the TLSA records, and the software which I do provide essentially tells us what is the usage, it's the selector and the type and the given fingerprint, of course. Yeah. So and from here we see the information we have gathered so far, and the first important issue is here: what is the usage? In the TLSA business, we have four different types of usages here. The most important usage is here that we simply look for DANE entries here, and that's by far the most usage here. What we do see here. That means people simply deploy the single certificate, and given the SMTP traffic, usually it's not important that you set up a certificate which is available in the PKX, but rather you can also use self-signed certificates. Nobody caring for that, actually, mostly. The response, the selector tells us essentially what is the coverage of the information in the fingerprint, and you have two different types here. The one possibility is that you cover the entire certificate, and the other possibility is that you simply recover the subject public key only. Yeah, and you see here that's a 9-to-1 behavior. That means people are feeling fine with the subject public key identifier. So the third information is the matching type, and here we can see that again. Essentially, people feel comfortable here using simply the SHA-256 hash sum, and only very few responses have been received where people using the SHA-512 hash sum. Although in theory and in practice, it's even much faster to operate here. So that means the DNS operators tend to prefer the SHA-256 hash sum here only. That's okay so far. So another question was, or another research result was essentially to see how many TLS records are available there per one single MX entry here so far, and we see that there is a 3-to-1 behavior essentially, that people feel fine with simply one TLSA record here, but by 30% we have 2 entries or even some more. Very strange results did happen so far. So that's yeah.
1 more minute.
Yeah, 1 more minute. So I'm also through. I'm almost through so far. Excellent. So okay. So what we actually find in our observation, and the conclusion is that the given MX records, what we have seen for the domains we have analyzed, we see a huge MX delegation. That means a lot of domains simply point with their email services to a third party, essentially, like Hotmail or Outlook.com. Yeah, in particular, those large domain providers here are in place. But also we see a lot of responses here given mailbox.org or protonmail.ch. This is a Swiss provider using postfix here so far. So actually, the most important information what we have seen here is TLSA coverage is simply strongly correlated with the behavior of that operators, of those MX operators. That means a lot of MX operators do not care about TLSA records, unfortunately here. Yeah. And so very few TLS records we have seen for China simply originates here from non-China providers so far. That means on the basic ground, the overall coverage of DANE and TLSA records is still marginal, what we have seen here, except for the Dutch domain. Yeah, and the policy people follow essentially here, given the usage here, it does not enforce for the mail clients essentially to look up the entire verification chain given the X509 certificates. Yeah. And also they feel fine with simply covering the subject public key identifier. And this has some practical consequences, since then actually we can avoid a lot of key rollover, what we have seen so far. And the final point is that the differences regarding the top-level domains regarding TLSA operations are mostly negligible, what I would say, and they follow essentially the same practical spirit, which are more or less laid out in the RFC 761, which was written by Victor, and people really follow these kind of recommendations so far. So that's essentially it, hopefully in time. Thank you for your attention, and I'm fine to answer questions now in the Q&A session.
Thank you, Erwin.
And here's the table of all our results, but I stop here with the resources and references.
We've got two questions from the channel. The first from Duane Wessels from VeriSign is, why was .com omitted from the study?
Oh, it was too big, essentially. I have to say, this was done on a very tiny server. The initial bachelor thesis took place on a Raspberry Pi 4, and we simply avoided this .com stuff, since we cannot manage this amount of information on that system here. In particular, I have to say that we observed a lot of misconfigured domains in the UK and net domain, which actually turned out to time out the entire query, and it was simply not manageable in our case.
Okay, thank you. And the second from Nils, it would be interesting to know how many users or email addresses are protected with the TLSA rather than how many email servers. Do you see an option to measure the impact on users?
Well, I could reanalyze the data. That would be possible. All the data are available. Yeah, could be done.
Okay, thank you. And back to Willem.
Okay, thanks again, Erwin. Also, thank you, Daniel again, and Niels again. We will now have a big break, 90-minute break, and the workshop will resume at 19:45 UTC or 13:45 Central Sharp.
We are back, and before we get to, I'm Suzanne Woolf from the OARC Program Committee. I'll be moderating the sessions the rest of the way. So if we are ready, our first speaker is Aaron Singaram, and he will be talking about implementing dual stack recursive DNS at Microsoft, challenges in learning. I'm looking forward to this. So Aaron, can you share your slides, please?
Hey everyone, I'm Arun, Senior Software Developer from Azure DNS. Today I'm going to talk about one of the recent efforts from Azure DNS team to increase resiliency of DNS resolver with dual stack. This talk primarily focuses on the process we followed, learnings and challenges we faced, and also benefits of enabling serve-stale data from cache. At Microsoft, we did extensive risk analysis for all the components for Azure to work seamlessly, and almost all of them have dependency on DNS. It is important for DNS to survive, even if entire Azure is down. This creates a greater burden on DNS itself to be extremely resilient. But how do we build this resiliency and achieve 100% SLA? There are things that are external to DNS, for instance, zero-day OS vulnerabilities that needs immediate patching, or dormant data plane bugs that get suddenly exposed in production. We decided to go with a dual stack implementation with following 4 tenets. We want both the system to be orthogonal as much as possible in terms of deployment mechanisms and DNS software used. We also don't want to use the same OS or even variant of same OS for that case. For example, we can use Windows, Linux-based OS, etc. We also wanted to use a combination of virtual machines and bare metal machines. That can be a bug in hypervisor, which prevents VM creation or updates. But at the same time, having virtual machines provides us the ability to quickly scale out in case of any emergencies. Currently, both virtual machines and bare metal machines are sufficiently scaled to handle the entire load if needed. This diagram shows the current architecture of our internal DNS resolver. Anycast IP is used to route traffic to nearest geolocation. This also helps workload that depends on geolocation, for example, DNS-based load balancer like Azure Traffic Manager. Currently, we receive close to 8 million QPS, and hardware-based load balancer is used to split traffic between the dual stack. Our unbound stack currently has the ability to advertise routes via BGP speaker. We are also evaluating whether to remove the hardware-based load balancer completely or have a combination of hardware-based load balancer and BGP speakers. At Microsoft, we have been using Windows Server DNS or WinDNS in short for a long time. For the purpose of dual stack, we are actually evaluating different softwares based on the feature set provided by them and also the performance testing results. We were actually spoiled for choices. In the end, we decided to actually go with Unbound. Once we decided to go with Unbound, we containerized Unbound. We actually integrated with Microsoft ecosystem in terms of safe deployment practices, setup monitoring alerts. We also enable query logging via DNS tab for troubleshooting any customer issues. Prior to launching the dual stack, we want to actually ensure both the serving plane response are identical as much as possible. Even slightest behavioral differences between the two systems can cause impact for our customers. We built a testing tool internally that can replay traffic from production query log against different systems and basically categorize the response based on differences into buckets and determine if the response are identical or not. Basically determine if the response are acceptable or not. We manually reviewed all the unknown differences and basically tweaked the tool to categorize them better. After several iterations, we arrived at the following chart. Around 86% of the response were identical. There were some acceptable differences like difference in how compression is handled or difference in RR set value in terms of IP addresses for AR quad A records. We have documented all the differences just in case if any of those differences lead to any customer issues. Overall, we are actually happy with the resiliency we achieved with Unbound, and we were able to actually remove single point of failure for DNS for our clients, but we did hit some roadblocks along the way. Even though Unbound is RFC compliant, some of our clients are not. One of our legacy proxy client does not support TCP, and they were actually piggybanking on the partial RR set records returned by WinDNS all along. So when dual stack was active, those clients were not able to resolve those queries. We also found an interesting bug with Unbound when QNAME minimization feature is enabled for domains with CNAME record. Basically in like a specific scenario. Unbound does not return IP addresses for domains when the domain is not present in Unbound cache, and we query Unbound for like a CNAME record first, followed by a record. Unbound just return the CNAME record set in that particular case, but does not return the IP addresses. QNAME minimization is a feature that is enabled on Unbound by default. We were also using some of the Unbound features incorrectly. For example, we were using Unbound reload instead of zone reload for some of the zone changes in our monitoring script. Unbound reload is like a costly operation since it flushes the cache. It took like around 8 seconds for Unbound to be online again in our use case. Initial investment to bootstrap dual stack is high. We actually had to do like a very slow rollout. We actually deployed to region with the lowest traffic first. And even within a region, we actually did like a gradual ramp up. For example, we did like 2% first, followed by 10%, 25%, 50%, and 100%. We kept it at 100% for some time to catch any issues that can potentially happen because of behavioral differences between the two systems. Our safe deployment practices actually helped in containing impact of the outage within like a single region in US for the TCP issue that I've actually discussed before. We also run perf testing as a part of every release to actually ensure that we don't regress on performance. Although initial investment to bootstrap the dual stack is high, the long-term maintenance is not always 2x. For example, for any feature development, I agree that we need to actually now go and develop in both the serving planes. But if you look at any feature development and release to the production, it's not always just the feature development, right? There are a lot of things that are surrounding the feature development. For instance, how we want to actually handle the testing or like writing spec test, performance testing, those things will be shared between the dual stack right now, and thus that by reducing the overall cost.
Okay.
One of the
Go ahead. You have 2 minutes until the Q&A that we reserved, but it looks like you're almost done. Thank you.
Sure. Yeah. One of the way to increase resiliency of DNS even further is by enabling source stale data from cache. Typically, recursive server amplify the impact of performance degradation in authoritative DNS server. Having ability to actually source stale data from cache will likely reduce the impact in such scenarios. Unbound actually provided this feature out of the box for us. This feature has already proved super helpful for us in reducing the impact of a couple of our zone outages. The following diagram shows the server file response from WinDNS and Unbound during the time of outage. As you can see, there is a sudden spike in server file responses from WinDNS, whereas the server file responses remain flat in case of Unbound. The impact could have been even bigger if not for Unbound and RFC 8767. This brings us to the end of our presentation. Hopefully everyone was able to get some useful information out of this. I'll be happy to answer any questions. Thank you.
So we've followed the first question from Brett Carr. It says, are you doing DNSSEC validation? And if so, did you notice any difference between Windows DNS and Unbound?
Currently, the recursive resolvers does not support DNSSEC validation. So we didn't actually yeah, that is out of scope for this task.
Yeah, okay. And the actual follow-up question from Brett was, if you aren't doing DNSSEC validation, what led you to that decision?
That will actually depends on our customer requirement. This is something that we are actually looking at it and will probably high on our list, but that is not supported yet. Yep.
Okay, thank you, Arunkumar. I'll pass back to Suzanne.
Thank you.
Yes, thank you very much. We appreciate that. Sharing that information. The next talk will be Duane Wessels on updating requirements for caching DNS resolution failures.
Hello, everyone. My name is Duane Wessels. This is a joint project with my colleague, Matthew Thomas. Today, we want to sort of hopefully convince you that there's this problem with caching of DNS resolution failures in the internet based on some of the things that we've seen ourselves and seen by other people over the years. So we see that, recursive name servers exhibit this aggressive retry behavior in the case of resolution failures. We've got a few examples with some graphs, and we want to talk a little bit about existing protocol requirements and make some proposals for updating those requirements in a new internet draft. So to set the stage a little bit, let's talk about what we mean by a resolution failure. Really, this means when a recursive name server fails to receive a useful response from any of a zone's authoritative name servers. So, we're talking about all of the name servers not being useful. If only one name server is timing out or giving the wrong answer, that's not really what we're talking about here. Examples of resolution failures are response codes other than no error or NX domain. Again, timeouts from all the servers, lame delegations, DNSSEC validation failures, and so on. We are not, a resolution failure is not an NX domain response or a no error, no data response. So here's some recent observations and also not so recent observations. To start off with, I'm sure folks remember from October last year, Facebook had a rather long outage of about 6 hours where in addition to some other things, none of their name servers were responding to DNS queries. The graph here shows the rate of queries to the ComNet name servers during that time for 3 different domains related to Facebook. Before the outage, I believe for Facebook.com, or maybe it's for all of them, We were seeing about 7,000 QPS on average. It's pretty steady down there on the bottom, at least at this scale. And then during the outage, the rate of queries increases and continues increasing until all in total, it exceeds more than 900,000 QPS. So this, we have a little bit more detailed write-up on this, including some similar outages on VeriSign blog. The URL is down in the corner there. In this case, we measured the increase factor at 128x. Last year, we presented some research at DNSOARC where we had found some domains used by botnets and directed them to a set of sinkhole name servers. And for one of those names, we intentionally configured it to return surfail responses from the sinkhole name servers. And when we did that, the traffic increased from 50 queries per second to 60,000 queries per second, as shown in the top graph on the right there. We also saw traffic increase at the upper levels of the hierarchy. So the TLD name server saw an increase, and we even saw an increase in queries for that name at the root name servers. But at the authoritative server, at the second level domain name server, the factor of increase was 1,200. So I'm sure folks remember the KSK rollover from 2019. That was a successful rollover, but there was this sort of interesting thing that happened towards the end where we started seeing a significant increase in DNS key queries at the root name servers. This data is only from ARoot and JRoot operated by VeriSign, but the other root servers did see similar increases. The significant increase started when the key was published with its revoke bit set. And when that revoked key was then unpublished, the query rates dropped down. So that was clearly the cause of this. The increase factor here was 80x, but that is just for queries of type DNS key for the root zone. A couple years ago, we heard about the Tsuname incident, where some cyclic dependencies were found in various zones. There's an example here where example.com lists an example.nl name server, and vice versa, example.nl lists an example.com name server. And if those are the only name servers, if those are in a cyclic dependency, then you get these, again, significant increases in query rates. And according to that paper, the factor was about 500x. Here's a few more, no graphs for these, but a couple of years ago, Victor Duchovny had a lightning talk at a DNSOARC meeting where he was talking about something he saw from his DNS surveys. Victor was doing surveys that ran for multiple hours, and as the survey progressed, he would remember which domains had a failure, and at the end he would retry all of those failed domains one more time. And at that point, retrying all those failed domains led to very significant traffic increases. The DINE attack from 2016 was a very complicated attack. But one of the characteristics of that was that they documented what they saw as a retry storm from recursive platforms greater than 10x the normal volume. Going back pretty far in time, December 2009, there's this very well-documented situation which is given the title rollover and die. This is when some in-editor ARPA zones had a key rollover, and name servers that didn't have that key, the trust anchor experienced very aggressive retry behavior. And more recently, there was a paper, an attack described called the NXNS attack, where in this case, the idea is that an attacker can intentionally use some of these aggressive retry behaviors to focus a large amount of traffic on an intended victim. So we want to say a little bit about the existing protocol requirements, at least as we understand them. One of the first things that you would encounter is RFC 2308, which has the title of Negative Caching of DNS Queries. This dates back to, I think, 1998. And one of the things it says in more ways than one is that negative caching should no longer be seen as an optional part of a DNS resolver. Most of the RFC focuses on NX domain and no data responses. It does talk about caching server failures and caching unreachable servers, but for those cases, it says that it's optional to negatively cache those conditions. We have BCP 123, which documents observed DNS resolution misbehavior, and it has a number of recommendations or requirements. One, it says that an iterative resolver must not send a query for the NSRR set of a non-responsive zone to any of the name servers for that zone's parent zone. So that's very similar to what we saw in the Facebook outage, although here it's talking about specifically a query of type NS, a query for the NSRR set. But what we saw in the Facebook outage was, of course, just the regular queries for addresses coming back up to the parent zone. This BCP also has a couple of recommendations saying that resolvers should cache name servers they discover are not authoritative, i.e. lame servers, and should take care to avoid sending queries at excess rates, should support throttling to detect when queries are sent but no responses are received. So those recommendations are in there, but they're not particularly strong. More recently, we have the serving stale data RFC, which says attempts to refresh from non-responsive or otherwise failing authoritative name servers are recommended to be done no more frequently than every 30 seconds. Again, just sort of a not a hard requirement, but a recommendation. And then because of all this and because of what we've observed, we feel that it's time to consider some stronger requirements. So this internet draft has been published, and we hope to present it at the next DNSOP meeting. But here's a little preview. Again, in the draft, we outline different types of resolution failures, most of which we've already talked about, different response codes, delegation loops included, alias loops, DNSSEC validation failures, and maybe even some others. One of the things that we say in our draft is that, and I don't think this is new. I think this is language is borrowed from somewhere else, but it says that resolution failures must be cached against the specific query tuple, the name, type, class, and server address. And if all known servers for the tuple result in resolution failure, then the resolver must not send further queries for the tuple until the corresponding negative cache entries expire. The draft has a little, some language about retries and timeouts. At this point, it says the resolver must not retry more than twice, which means 3 queries in total, before considering a server unresponsive. But it doesn't place any particular requirements on timeout values, which could be implementation dependent. But we expect that generally, timeout values would range from 3 to 30 seconds. To get specific on negative caching TTLs, we suggest that resolvers must cache resolution failures for at least 5 seconds and should employ an exponential backoff algorithm to increase the amount of time for subsequent resolution failures, and that must not be cached for longer than 5 minutes. So 5 seconds to 5 minutes is what we would suggest for negative caching TTLs. And then getting back to the the event from Facebook, we really want to reiterate the requirement from BCP 123 about requerying parent zones. So this graph on the right again is from that same event, but it shows the rate of queries from a single recursive IP address during the event. So we were seeing 1,500 QPS for Facebook.com from one IP address, which is just ridiculous. So we don't have, I don't think we have perfect language on this yet, looking for some feedback, but I would definitely like to strengthen the requirement about requerying delegation information. So there's the name of the draft. Hopefully we've been able to convince you that this is a problem that needs addressing, and would love your comments. And happy to take any questions.
Okay, thank you, Duane. So the first question from Peter van Dijk. Many resolvers currently have code to briefly stop querying authoritative that have trouble responding at all. This helps mitigate attacks mounted through those resolvers against those servers. The tuple, which I spot in 2308, sounds overly specific for that case. Maybe it's time to relax that requirement.
Yeah, I would have to. Off the top of my head, I don't know exactly what he's referring to, but that sounds reasonable to me. Happy to take a closer look at that and agree about changing that requirement if it makes sense.
Okay, and from Tail, for reiterating the requirement from BCP 123, could you please just make it a general do not query the parent instead of the current language that restricts it to just type NS? Most delegations are discovered not from explicit NS queries.
Yeah, that's what I was thinking as well. I'm not sure why BCP 123 focused on NS queries. I don't know if there was a specific case where they found that happening, but I agree. I think any queries of any type back to the parent should be restricted.
I see some people typing, but I don't know whether they're typing questions.
Yeah, for anybody who doesn't normally pay attention to internet drafts, just to add a couple of notes. This is Suzanne. Just for folks that don't necessarily spend a lot of time reading internet drafts, all you have to do is read them and comment. You can comment directly to the authors or on the working group mailing list. This one will be introduced in DNS operations, but the feedback is really, really important, particularly from operators and implementers. So that's today's commercial for making protocol documents better.
Okay, and we do have another question. I thought we did. Another two, here we go. So for this is from Otto M. Should negative caching include unparsable or other faulty responses?
I think that's worth considering. Yeah, I guess I would say that that's not something that we've seen evidence of it has been a problem, but on the surface it sounds like a reasonable thing to do. Yeah.
Okay, thank you. And from Jeff Houston, can you comment on the variation between the approaches of a recursive resolver to fail fast and fail hard versus exhaustive search?
Probably not. I'm not sure. Is Jeff? I wonder if you're referring to like suffix prepending, that kind of search, exhaustive search, or are you talking about searching through all the different authoritative name servers? If it's the latter, at least in this draft, we're not proposing that like a recursive, try one or two authoritatives and then give up.
Jeff says DNS, for DNSSEC validation in particular.
So I think I understand what you're saying, Jeff. You're talking about if you get a DNSSEC validation failure, should the recursive, try at another authoritative name server? And I agree that that is probably one of the reasons we see a lot of aggressive behavior from like in the case of the KSK rollover and the rollover and die and that sort of situation. I don't know. I would like, I guess, community input on that. What people think. I think as far as I know, different implementations take different approaches. Some will try exhaustively, and some will try less exhaustively. So I guess we would love feedback from implementers on that.
Okay, and from Puneet Sood, can you comment on how much of the problem in your experience is related to a small number of large resolvers versus many resolvers being somewhat chatty?
So thanks, Puneet. Definitely, we do see this behavior from I would say the bulk of the behavior is from a small number of recursive resolvers. We haven't, unfortunately, sort of done a more broad analysis on, if we eliminated those one or two really problematic ones, then what do the rest look like? I think that not everyone is off the hook, but I think some are maybe a little bit more guilty than others.
Okay, I think that means we're out of questions now. I don't see any more. Thank you, Duane. I'll hand back to Suzanne.
Thank you very much, Duane. So next up is Ed Lewis talking about implementing wow. I need to get to the right place in the schedule. Thank you very much. Beta availability of 2 TLD data products. You may share your slides.
Okay, this is the beta availability of 2 TLD data products, and my name is Edward Lewis. I work for ICANN, and I'm going to present on this topic. Now, the purpose and agenda of my talk is captured here. The upshot is I'm making 2 data products available, and the availability is in a beta state because really haven't had a lot of time to give any road trials, and so the community here is probably the best place to find people that will be willing to take time to test this stuff. And I have 2 data sets there. One's called the TLD Apex History. The other is called the DNS Core Census, and I have a version number in parentheses there. I'll explain those 2 later on, but those are the 2 things that are being made available. Now, the goal for me in all this effort is to make these data sets be they're continually updated daily basis, not continually like a live stream, but definitely not any stale data out there. Data is going to be updated every day, at least once a day. And I also want these data sets to be very accessible for scripts. Scripts or programs to access the data in it, as opposed to visually stunning graphics for people to see. And I'll get into why later on. So in the rest of this talk, I'm going to talk about the TLD Apex History, what it is, what's the data that I'm going to present, why it's interesting to people, and then why I consider this to be a beta program. And then also for the DNS Core Census, I'll talk about it. I did actually present the DNS Core Census concept at DNS.org about a year ago. So I won't spend a lot of time trying to dive into that, but I will talk about the data that I'm releasing and what makes it a beta for that also. So to the first level of scene setting here is that there's a lot of information available out on the internet, and a lot of it's in web pages, and they seem to be aimed for people's eyes. And I've had a hard time. I've been scraping websites for a long time for their tables, and it's very apparent that computers see differently than humans. White space that humans don't know about bothers computers when they try to parse information out there and data types and so on. It's not that easy to get the data out of a table into a computer program. It should be easier. There are also a lot of DNS information sources out there. Metadata about the system that's going on. That's where I'm kind of floating around in. The metadata helps drive the analysis later on when you take other data sets. This data is scattered. It's all over the place. So I wanted to get that into one place because I constantly have been looking for something, and you have to look everywhere to find that one thing. Now, probably the reason why the world's gotten to this state is that we do a lot of short-term projects in research, a lot of presentation type work. We do dissertation type work. We really need to have long-lived measurements to help us go down the road as the internet's maturing. It has been maturing for quite a while now. So I just want to get to the point where my data is constantly being updated. It has a long-term life to it, and it's helpful day to day, and also going back in history. So the aspiration is to aggregate all this data in a structured format and support the long haul. So now the immediate driver, what launched me on this effort for the past couple of years, actually kind of coincided with the pandemic reactions to travel, being able to spend more time with my computers. When I'm looking at TLDs, know the top level names, I always have to divide them. Are they GTLDs or CCTLDs? Because that matters when you do an analysis of what's going on there. IDNs also. We like to look at different categories of TLDs out there and why do some behave a certain way. We have things like this DNSSEC. Are they signed or unsigned? How do they behave differently? Some people I work with are concerned about groupings by geographical region. And I should say I'm not going to get into IP geomapping. That, that's a lost cause. But there's some things we can categorize by where they are based on the registration information. And also, with some of this work, I've been able to see some of the inner workings of the industry. We talk about these times when many things go down because some underlying platform fails. There's some of that evidence some of that can be measured by looking at some of the data that I'm releasing to take a look at that. Now, the data sets that I'm getting out there, they're not judgments, they're not top 10s, they're not gradings or rankings. They're trying to be complete collections of references out there, more like an encyclopedia rather than a newspaper article. And the data, a lot of the data is, of course, coming from ICANN sources, because that's where I work. But I'm also pulling in data from other sources too into this. Now, this slide here has a bunch of URLs, and this is basically the upshot of the whole talk. The website I have up is crude. I don't have HTML up there, but I have these links, these actually directories where there's going to be information. And I'll go through this in further slides, but just if you have to come back to one place to see all of the URLs that are of interest in looking at this data, this is the slide to find them all together. Now, one of the things that's I've been working on the last couple of weeks and actually held up my slides from being an early delivery was licensing. When I was putting this work together, I was asked about the licensing of the data that I'm using. And usually, generally, people don't have any license information published about the data that they are releasing. There's nothing saying what you can use it for, who can't use it, where you can use it. And so I've been motivated to at least kind of put a stake in the ground and say, we're going to start putting something out there. And so I'm after, right now, we don't have a license decided upon yet. Right now, we're discussing that, and I haven't been able to get a resolution to this. But I'm looking for a license, and what I would like the license for this data to be is, and for any purpose out there, though I may not have the final say on that, public or commercial. It doesn't matter with this data. But also realizing the data may cease to be updated at any time. And there are glitches, and there are problems I have with some of the code. I'm doing this basically right now as a solo effort internally. And also the data may be pulled off. We may decide that the data wasn't a good idea to put out there at some point, depending on who reviews the data and so on. Nothing out there is under question, but you never know. Someone might say, we don't want to have that stuff out there. So this is an effort to get people to take a look at the data, and it may change over time. And as soon as we can formalize our terms, we will have that up there. So now I'm going to have two slides here about the layout, a little one level down in the information here. I have for the TLD Apex history, there's a table directory, and below, and inside of that there are two files. One's JSON and one's CSV. I don't know which is better, CSV or JSON. I just produced both of them right now. They both have the same exact information. If you use certain packages for reading these two, you'll get the same information out of it. I just think that some people like JSON better. JSON seems to be preferred. It's more visually stunning, but it's a lot bigger. So that may fall off. CSV might still be the best way to transit tables around between researchers. There's a doc directory that has a data dictionary in it to help explain the data out there. This data may not be apparent when you first see what it is, but of course everything needs to have an explanation. So there are some human eye documents there, and then there's a code directory, and this right now is an example in Python 3, a script which pulls the data off the website and prints some information about it, just to illustrate how you access the data. For the DNS core census, I have pretty much the same structure. I have a version 010 tagged in there because there have been other versions around here and there. The table directory has a catalog file in CSV, and then it has a rolling 35-day window of the census runs. I'm concerned about disk space at this point, so I'm putting out 35 days. Might be give you enough time to play with the data out there. There is a lot more data available. It's just a matter of what can we put out there without blowing up the disk space and such we have out there. The doc has data dictionaries also. There are 161 columns in these tables. That's why there's actually 9 tables. A lot of information in there to try to explain, and a lot of error information to cover. And again, I have a Python example in the code area which pulls the one of the census reports out and displays as much as it can, just to give you an idea of what's in there. The code itself is not necessarily elegant. It's just trying to show what you go through to pull out the information out there. So TLD Apex history, why is this interesting? Yeah, a couple of slides on that. It started out with looking at DNSSEC and saying, well, how do people roll out DNSSEC? And so one of the ways to do that is to look at your peers. This was not the start of DNSSEC, but there had been a couple examples out there already. And so we just took a look and see what do people do here and there. It's been able to kind of reverse engineer how operators do DNSSEC by looking at a couple of records at the apex, the SOA record, DNS record, the keys, the DS and the NSEC record, only at the apex. It's been a pretty easy way to, the pretty small set of data that's needed to actually start figuring out how DNSSEC is configured. Now the history is a single table. It's updated every day. It's based on a number of runs that are done. I do somewhere between 12 and 24 runs a day looking at things, and I just aggregate this. So, and it looks for, is a record there on a particular day? And I have a database entry says, here's a record, and here are the dates it's seen. Usually they're in streaks, in consecutive days, and so on. The data does not cover validation. It doesn't talk about operational things. This is purely trying to capture how someone has decided to configure DNSSEC, not how they pull it off. That's why it's not really good. This is not data for judging or competing operators against each other. Now, the data has been around for some time. There's a couple of years of it being made available right away. The benefits for this briefly are for operators. When I've used this data talking to some operators, it's interesting to see their own track record and records of others who do similar work to them to compare, do they think they need to do something more quickly, less quickly, and so on. For protocol developers, it's interesting because this really helps quantify the deployment and what gets released, what's being used, and so on. Like, for example, a while ago, there was some question about the NSEC 3 iterations was an issue for a little bit of time, and you could look across and see what the TLDs have been choosing to do for some time. Now, my favorite toy with this is visualizing key life cycles. This toy isn't being released. I've given a talk or two on it here and there, and I'm going to come back to this now that these things are available. You could take the data in this table and just start drawing on a plotting out how keys are rotated and managed by an operator. It's interesting to look at some of the unusual events that happen in there. There have been, and some of the protocol developers that have looked at this were surprised by seeing some keys seem to go away and then come back. Some operators aren't shy about reusing a key that they had retired. There's nothing really wrong with it, but it wasn't expected to be a way that would be run. And there was, and to my surprise, one time when I ran my tool across all the data all the time for whatever, I found one example of a TLD that actually had 2 different keys with the same key tag in action at once. I don't know anything about that story beyond that because I haven't been able to talk to them in the last couple of years. But I never heard complaints about it, and it was apparent that they had changed things based on. It's just apparent they changed things. I can't really tell you because without having talked to them, what happened. So the beta questions, things like, is the JSON format necessary? Do we really have to? Is it just a cool thing for kids? I don't think that JSON adds much to this, but I'm willing to learn. A good question, though, is, are the records that are being presented here, are they sufficient? Are they enough of what we have out there? Is it too much? What other data should be included? For example, one thing I've been aware of is a zone MD record, which isn't DNSSEC, but that is information that we could include in this. By the way, there is one TLD that does a zone MD record out there, and I managed to have been looking for that before they started. And finally, also, should we try to expand the coverage? I've only done TLDs. That was just basically the start of this years ago. But we could look at some other places out there. I tend to stick to the TLDs because it's kind of a quantified set of data. I don't have to judge who's in and out of TLDs. I refrain from picking social media sites or content providers or whatever, because that gets judgmental about who does or doesn't belong to this study.
Ed?
Yes.
Pardon the interruption, but you have 5 more minutes till Q&A.
Okay. So DNS core census, this is a less mature set of data. It started out with me trying to decide whether xn -- example was a CCTLD or not, a GTLD IDN. It's very hard to tell that. Also, I wanted to be able to look at all of the TLDs belonging to a region. For example, India has many IDN CCTLDs out there. And trying to get that list all the time was always kind of a lot of work. A lot of information spread out all over the place. IANA's web pages, ICANN's web pages, other non-web page information ICANN spits out, the region information, and so on. And plus, I expand this to go into ROA coverage, looking at how ISP information is used, AS numbers, and so on. And then even trying to go out to what I call the commercial registration boundary. These topics take way more time, and they were a talk to themselves already once. So the DNS core, briefly, TLDs, what's in ARPA, the things that the RIRs manage, and then sub-TLDs, and down to what I call the commercial registration boundary. The census is an aggregation of information from all over the place. And I have in italics there what is considered to be useful. That's a very subjective thing. And of course, that's a hint that this is beta. I'm willing to look at what should or shouldn't be in there because I've just made some of these judgments that I ran along. And each run has 9 tables because I couldn't flatten it any better. So right now, 9 compressed CSV tables. It's large. That's why I'm limiting how much I have out there. It's, again, this information here I had earlier, code, the doc, and table directories. And the only compressed, let's say again, size constraints are why I only have information there. If it turns out this information is really helpful, we can look into expanding this. But right now, I'm only putting out a little bit of the data out there, enough to take a look. Version history, the reason why I talk about version 010 in the slides is that there's a 002. That data is available somewhere, but I don't publicize it anymore because I've stopped collecting that. I don't know whether I'm going to translate that into the 010 format. That's a possibility. And that would give us data going back to much earlier in time. I forget when I started that one. Probably about a year or 2 years worth of data. So 010 is out there. It's been running since May 2021. And again, you only have 35 days for the time being. Now, why publish this? The frustration I had with getting HTML tables into computer readable formats was one driver for this. I've also had to find new sources of data. Some of the data sets that I've been pulling from went away, and I had to replace them. And sometimes there were some gaps there, and I need to be better at that. So that's where this is. It's still trying to figure out what's the best way to do this in a stable way over long term. It's a lot harder to aggregate the data, and I will just skip over that. Finally, the experimental arms of this work are the determination of the commercial registration boundary that I mentioned a couple times here in another talk, and also whether or not we go down to like the ROA information and name servers. Is that really part of this, or is that something where that's too dedicated to one specific purpose I had out there, and maybe I should not bother so much there. The beta questions, what's there? Is it useful? Is there needless things out there? What should be included? What should be added? Is the non-data elements like not every TLD is in every one of the databases out there. So all these so-called error messages, are they helpful the way they are? And one thing that I've become very attuned to in the last few months is there's got to be a better way to store this stuff. It's good to have the history out there, but it's taking up a lot of disk space as I'm running this right now. And I have been learning some new ways of attacking this problem. But the question is, of course, will I do that? Is this information useful enough to go through that expense? So, benefits and costs of this audience. I really wanted to get this in front of DNS-org. That's why I was pushing through recently to get this done and up and running without answering some of the questions I had. The intended benefits, I think it's a consolidated reference for information. If you do any kind of work where you want to know whether a name belongs to a GTLD or CCTLD or it belongs to some CCTLD somewhere on the earth, this would be helpful. It's providing a historical recording of the state of the core, what has happened over time. And it's trying to get the data from authoritative sources or direct observations here. I cover GTLDs much more thoroughly in the DNS core because I have much more information from ICANN. CCTLDs, even though there are some that I could get zone files from, I shy from that just to make sure it's clear that this is the data I really have, and this is data that could be added over time. The cost to the audience, this is beta. I mean, if you start playing with this, it would be very helpful to me, but we may decide that something's got to change and you may end up winding up having to re-implement some of the parsing over time. And so with that, I will say that the feedback as it comes in right now, I don't imagine there's a huge demand for this stuff, but so email can come to me directly. Maybe later on we'll see whether or not this is more useful data and we might want to set up some other way of communicating amongst the group. But if you're interested in this data, give it a try and let me know what you think. And that's what I'm asking of you, and I should be about done now.
Okay, so the first one has been phrased as a question, but is really more of a statement. Ed, will you please use JSON and not CSV? And I should say from the chair here that that is overwhelmingly what's been requested on the chat, with JSON actually being far better specified than CSV and actually therefore easier to parse.
Yeah, I think if you take a look at the data, I understand the sympathy for that. It is a huge, JSON is eight times the size of the CSV. And it's something we can be discussed over time. I think JSON is more wonderful. Let me put it this way. The problem, okay, so this data is row column data. It's very flat. And I'm doing that with the mind of trying to get into some of the other platforms out there that deal with tabular data. And the very richly structured JSON data that I used in 002 of the census, I couldn't get that data into these other platforms, like other open data products out there. They couldn't accept the data. It seems like, as much as it's like being a Luddite here, CSV is much more useful in getting this into other platforms out there for like open data and whatever. So that's part of the discussion here. And that's, I can continue with the Apex history, it's small enough that I'll publish both. And it is much easier to look at the JSON to figure out what a field means than what CSV does. That's certainly true. When it came to the disk space for the core census, at 8 times, and right now I have it compressed, and then so that's 10 times, and 8 times that would give you an idea of how big JSON was getting. So I would say JSON is very elegant and great for data structures, but it's very hard when it comes to passing tabular data between different things like either backend databases out there or open data out there. That's a consideration, and I think it needs maybe some more debate than. I mean, I understand JSON is much prettier to look at, but I've dragged myself back to CSV because every tool around me wants CSV. So
yeah, I mean, to be fair, we haven't actually seen the data yet, so it's a bit hard to judge. But,
yeah,
and I'm going to jump down a couple of questions here because it's still relevant. And said, yeah, if your concern is storage efficiency, have you considered using JSON but inside of gzip or bzip or some other compressed file?
Well, I'm using gzip on CSV, or as it is. So yeah, that would just bring it down an order of magnitude. But there are some other things that are going on here. Let me give you a hint. Every day I record the signature files, signature records rather. And for most of the data in the core, it doesn't change day to day. So I could probably just have the signature records in one massive table and reference that. So it gives you an idea of what the problem here may not be that straightforward. I don't want to eat up the time now to talk about it. Just
yeah, we do only have a couple of minutes now.
Yeah.
So from Sebastian Castro, have you considered offering an API endpoint to allow simple queries over the data, such as give me this data set after this date?
Let me okay, so what I want to do first, I want to establish that there's interest in the data before I try to fight the battle to get something more up and running, to get a deeper investment in this. And I guess that's pretty much what I'm after right now. If we can find, I mean, I understand. In fact, I have designs on having this data available in other formats, but I don't have a justification for that at this point. That's the help I really want from people to say, if you like this stuff, there can be more of it. We have to figure out how to arrange for that.
Okay, and this is going to have to be the last question because of time. Where's it got? Nils. Yeah, so how do you collect and store data? I believe there is some community demand for good collection tools.
Well, I start out with homegrown scripts to get stuff. And then I bring it in somewhere, and I munge it just a bunch of different ways right now. It's mostly, I do a lot of, I'm a programmer by nature. So I tend to use more of my own Python right now. And I just, right now, if you looked at my stuff internally, I will take data in, I will munge it, I will massage it based on having, also a lot of domain knowledge, I have to admit. I've worked 20 something years with TLDs. So once I do that, I store it all over the place, CSV, JSON. I have it in some backend online cloud databases, trying to find out what can I get away with? What's the best way to deliver this? And also the website pretty much is it's the most convenient vehicle I have with which to get the data out to what I can call stakeholders or the public out there. So it's we're searching to find out what's the demand, and then from that we can decide whether it's better done with tooling out there, something else we have to go out and procure.
Okay, thank you, Ed. We're out of time for questions now. There are still a couple of questions outstanding on the workshop channel. Maybe if you engage there to address those, please. And I'll pass back to Suzanne. Thank you, Ed.
Sure.
Thanks, Ed, and thanks, Ray. Next up, we have Carsten Strotmann to talk about IP fragmentation and DNS cache poisoning. Could you go ahead? Aha, you are already sharing your slides. I can see that, no problem. So please go ahead.
Thank you, Suzanne. Hello and welcome. My name is Carsten Strotmann, and I will talk about Frag-DNS, IP fragmentation and measurements against DNS cache poisoning. So this is actually a report based on a study that was contracted by the German Federal Government Authority for Cybersecurity between December 2019 and September 2021. And in the team, we worked with Roland from Rijswijk, Mr. Patrick Kötter, Marcus de Bruyn, and Anders Curligan. And the questions that we want to answer here in this study is, does DNS cache poisoning via fragmentation impose a real threat, or is it more theoretically? And is it possible to mitigate these attacks, and how effective are these mitigations? Now, the study will be published in April, and it's some 70 pages, and I will only have time to highlight some of the aspects. There's more details in the slides that I cover, and also there will be much more details in the study once it will be published. So, cache poisoning via fragmentation. Very quick, what is this about? An attacker can lower the path MTU between a DNS resolver and an authoritative server by doing ICMP spoofing. And then once a DNS query comes in via a resolver, and that DNS response that has to be sent on the DNS query is larger than the path MTU that has been lowered by the attacker, the sending authoritative server must fragment. The attacker knows that and sends already ahead of time a spoofed DNS answer as a second fragment. And then the original or the good first fragment is being sent by the authoritative server. Resolver is combining both the second and first fragment to create a complete DNS message, and that is being sent to the client who gets a wrong answer. So what we wanted to know is how much of IP fragmentation for DNS responses really happen in the real world. So what we did is we did a measurement on a large German ISP DNS resolver, which 4 million home and business internet access customers. And we specifically looked for how many DNS responses came back to that resolver that were fragmented. And we found that 0.1% of all IPv4 responses got fragmented, and 0.11% of all IPv6 responses got fragmented. And the big majority of these fragmented DNS answers came from DNSSEC signed zones. This is the plot of the amount of DNS fragmented answers over 24 hours. This is the total numbers of fragmented messages, both IPv6 and IPv4, and we see there are a little bit more IPv6 fragmentation happening than on IPv4. And this is the percentage of the total amount of DNS responses seen in the time frame. And we see here a little mountain between 4 and 8 o'clock in the morning. And this is something that might be interesting to research later on. Then we found that only a limited number of DNS name servers out there in the internet are responsible for the majority of the fragmented answers. We found 133 name servers accounting for more than 90% of all the fragmentation over IPv6, and only 37 name servers are responsible for 90% of all the fragmented responses on IPv4. Now, when we see these low numbers compared to the vastness of the internet, we can think, oh, this is not really a problem. This is probably something that we can ignore. But a deeper look into what kind of DNS servers that were and what domains being hosted there revealed that there were some interesting ones, and we picked here a few like FedEx, like Fraunhofer Gesellschaft, or army.mil or office.com. So these are not domains that we can just ignore. Next, we checked if we would see fragmented DNS responses from authoritative DNS servers, and we used the Open Intel platform for that, which is a research platform that collects millions of DNS data every day, and it observes about 60% of the public internet. And we've seen there from the queries for SOA records, A records, NS records, and DNS key records that we see 0.047% fragmented responses over IPv4, which are 1.3 million responses on the total responses seen in one day. And on IPv6, it was 0.096%. So again, in percentage relative to the complete amount or all amount of responses, this is very tiny. In the numbers, it's high still because the internet is big. So what we've seen here is the response sizes, the sizes of the DNS datagrams over IPv6 that we have seen in this measurement. And we see most unsigned responses are below 512 bytes. Very few are larger than 512 bytes. And from the DNS signed one, the ones with DNSSEC signatures in there are below 1,232. Only a very few are higher than that. And the ones with DNS key are a little bit more than the ones just DNSSEC signed, but still below 1,232 or 1,472. And the same for IPv6, which is a very similar picture. For IPv4, sorry. This was interesting. We then looked what kind of message sizes were advertised by eDNS buffer size. And there we've seen that almost 50% of all the internet authoritative server there already did some changes away from the then default for the open source DNS servers, which was 4 kilobytes at that point of time, down to other values, something like 1,472 or 1,220, 1,232 or 1,280, which is the IPv6 MTU. There were 2 bumps at 1,680 and 2,800, which we couldn't really explain, and that might be an interesting research topic for later. So then we looked into what happens if a DNS answer is too big, and we maybe as a mitigation want to lower the UDP response size to something that is guaranteed to not fragment, like 1,232 byte. Then larger responses will go over TCP. How many authoritative DNS servers out there in the internet can work over TCP? Again, we used the Open Intel platform for that, and we found out that the large majority of authoritative DNS servers, 97.57%, have at least one DNS server offering DNS over TCP. And even 90% of all domains are hosted on DNS servers that have all their authoritative servers over DNS. And then a small percentage, 2.4% of the DNS servers that we've seen in the dataset had no DNS server supporting DNS over TCP. So almost same picture here. The majority of the internet is good. There's a small amount of DNS servers that don't support what's needed in the modern internet, but still the number is too large to really ignore that number. So we found even some very popular domains such as live.com, office.com, and yahoo.com that did not have TCP enabled on all their authoritative servers, at least at the time when we did our measurement. Some were fixed later on. And in total, we found that 1.5% of all the domains in the Tranco 1 million list do not have TCP support on their authoritative DNS servers. And then the question is whether that is on the 1 million Tranco list, whether that is on the lower end or on the more popular end in the beginning. And we found that it spread through almost all the ones. The very early 1,000, let's say, they are all good, but then in the middle, in the belly of that curve here, we've seen that we have servers that either have no name servers with TCP or just have one name server, or where at least one name server doesn't support TCP. So conclusion here is that a few, but also some popular domains do not support DNS over TCP. And so the use of DNS over TCP as a mitigation to mitigate these kind of attacks is not recommended. So meaning switching from UDP to TCP completely doesn't work. Then we looked into what operating systems are vulnerable to these kind of PathMTU spoofing attacks. We installed in a lab environment several operating systems, popular operating systems, different versions of them, and then tried to launch this attack. We tried to spoof ICMP packages to see whether these operating systems will reduce the PathMTU. And we found that especially older Linux systems, older but still in use because they are kernel versions that are still used in long-term supported Linux systems, are vulnerable. These older Linux kernels could be spoofed into having a minimum PathMTU of 552 bytes on IPv4. We also found that FreeBSD, OpenBSD, and the Windows are not vulnerable at all, or at least we couldn't lower the MTU there. We found that on IPv6, we could, for all operating systems, lower the path MTU to the minimum allowed by IPv6, which is 1,280 byte. And that was expected because the RFCs demand that that is possible. And then we looked, and this is not really good science or very accurate science, but we just were curious how many people run DNS servers on these old operating systems. And what we did is we queried the version data from the chaos class version.bind, and we checked there some Linux distributions have the version number of the Linux distribution encoded in the bind version number. And we found that from the Red Hat Linuxes, for example, which seems to be the majority of servers in the internet where the developers or the administrators haven't switched off the version information, there are still a couple, like more than 10% Red Hat Enterprise Linux 5 and 6, which are vulnerable.
Yeah, Carsten, you have 5 more minutes before Q&A.
Thank you. That is in time. So we tested several mitigations, and I will not go into all the details here about the mitigations. The more detail is in the slides, and I'm happy to answer specific questions in the chat later on. But for now, I want to go into the conclusion, what we found. We found that the best mitigations from the testing that we did is what has been implemented in the October 2020 DNS Flag Day, which is to reduce the response size for DNS responses to 1,232 byte. And at the same time, after doing that, block all fragmented answers in the firewall. Because once there is the response size reduced to that value, there should no real natural DNS fragmentation appearing. And all fragmentation that then appears is very likely intact. And we tested that over the 2-year time at these German ISP, which is a really large environment. We filtered in the firewall all fragmented DNS responses during that time, and we had no negative impact on that resolver infrastructure. So other takeaway is popular domains are vulnerable, and fragmentation of DNS responses should be avoided if it is all possible. And that can be done by lowering the DNS buffer. And also, of course, mitigations against DNS fragmentation is just focusing on the effect, but does not eliminate the cause of cache poisoning. So this should not be an excuse to not implement DNSSEC, of course. And with that, I'm open for questions.
Yes, thank you, Carsten. And it's Ray Bellis's turn as the Q&A monitor.
Yeah, thank you. Thank you, Suzanne. Actually, as far as I can see, we have no questions from online and none in here in the room either.
I will be in the Mattermost if any more questions may come up.
Okay. Oh no, we have one just come up.
Okay, good.
From Nils, how did you measure TCP support, and did you look at resolvers too?
No, for TCP support, we used the OpenIntel platform. Is a system that probes 60% of the known internet, and with that, it tried to reach port 53 UDP and port 53 TCP of all the authoritative name server it has in its database, which is roughly 60% of the internet's DNS servers. And we tested whether we got a positive response or the same response back over TCP that we got over UDP. And we didn't test resolvers because we can't from the outside, else it would be an open resolver.
Okay, and another new question coming from Ralph Weaver. Did you analyze the block fragmentations to see if they were attacks or misconfigurations?
We looked a little bit into the data. Most were misconfigurations. We've seen a lot of TXT records in the apex creating the fragmentations. We saw some instances of larger than 30 NS records in the NS resource record sets that creating the fragmentations. We at least saw one instance of fragmentation that looked like an attack in a 24-hour measurement, that is.
Okay, thank you. And a clarifying question from Peter. I don't know which Peter. Actually, this is still need this here. In the ISP test, did you capture the blocked fragmented packets for inspection? I think you've maybe just already answered this.
Yeah, during the test, we set a special firewall filter where we captured all the fragmented packages into a TCP dump file, a PCAP file that we otherwise would just throw away.
Okay, thank you. Okay, seeing no more questions, I'm going to hand back to you, Suzanne.
Thanks, Ray. Thank you, Carsten, very much. And we have for our final speaker today, Kazunori Fujiwara, pardon me. An idea of IP Anycast analysis using DITL dataset.
Hello, this is Kazunori Fujiwara from JPRS. I will propose an idea of IP Anycast analysis using DITL dataset. To analyze the effectiveness of IP Anycast, we need to know location of each server instance, location of each client, and latencies between each client and each root server node. DNSORC and root server operators collect 50 hours of packet capture at root DNS servers once a year. I would like to use the dataset to evaluate the effectiveness of IP Anycast. Guessing Anycast node location from DITL dataset. DITL dataset is located on DNSORC's analysis servers. Directory names may contain Anycast location name, base directory / dataset name DITL 2020-0505 / clean / letter -root / node / datetime.pcap.gz. Node patterns depend on each letter. Typical node patterns are here. mroot case, mroot -area, and optional IX name. mroot uses the airport code of the neighborhood as the instance name. And mroot server's org page shows mroot locations. Tokyo 3, Osaka, Seoul, San Francisco 2, Paris 2, Brisbane, Hanoi, and Guam. From directory name, there are 10 names in DITL 2021 dataset. BNE, Brisbane, Australia, ICN, Seoul, Korea, KIX, Osaka, Japan, NRT, Tokyo, Japan, CDG and ORY, Paris, France, SFO and SJC near San Francisco. And how to retrieve query latencies. DITL dataset contains packet sequences of complete TCP sessions. SYN, SYN-ACK, ACK, DNS query, DNS reply. Each timestamp is captured at the server. If TCP protocol stuck and DNS software send the next packet immediately after receiving the previous packet, the RTT is calculated as the sending interval, timestamp of ACK minus timestamp of SYN, or timestamp of DNS query minus timestamp of SYN. After this slide, preliminary results are shown, and there are many limitations. These graphs show mroot 2021 queries average RTT by continents, countries. 40% of mRoot queries come from Asia. Average RTT is 105 milliseconds. 30% of queries, 30% of mRoot queries come from North America, and average RTT is 70 milliseconds. 23% of mRoot queries come from Europe. Average RTT is 49 milliseconds. 3.3% of mRoot queries come from South America, and average RTT is 185 milliseconds. It's too long, I think. And 26% of queries come from United States. Average RTT is 66 milliseconds. 7.2% of queries come from India. Average RTT is 147 milliseconds, longer than 100 milliseconds. And 5.1% of mRoot queries come from Japan. Average RTT is 7 milliseconds, very short. These graphs show mRoot 2021 RTT query cumulative distribution function graph by continent. Vertical axis is CDF of query of number of queries, and horizontal axis is RTT in milliseconds. The graph above contains queries without TCP RTT data. Queries between each client and each root node are UDP only or TCP without complete packet sequences, about 35%. For a quick comparison of RTT, the following CDF graph ignores data without RTT. mRoot offers short, smaller than 100 millisecond RTT for over 90% of queries from North America and Europe. Over 70% from Asia, over 60% from Africa. However, over 100 millisecond RTT for South America and 35% of queries from Oceania. And the graph above shows CDF of RTT and number of queries. The graph below shows CDF of RTT and number of client IP addresses. For all queries, 79% of queries, 71% of IP addresses are shorter than 100 millisecond RTT. From Japan, 92% of queries, 73% of IP addresses are shorter than 10 milliseconds, very short. From US, 95% of queries, 79% of IP addresses are shorter than 100 milliseconds. From Australia, 35% of queries, 57% of IP addresses are shorter than 100 milliseconds. From New Zealand, 16% of queries, 16% of IP addresses are shorter than 60 milliseconds. However, others over 150 milliseconds. And this graph shows queries average RTTs by countries observed at mRoot Paris node. This graph shows that IP Anycast seems to work well. Paris node provides short RTTs for Europe. Next graph shows the effectiveness of mRoot Brisbane Australia node. mRoot instance launched in Brisbane on 18th December 2020. And these graphs show which node the queries from Australia sent to mRoot and average RTT. DITL 2020 dataset before launching Brisbane node, 52.8% queries from Australia were sent to Tokyo node. Average RTT is 181 milliseconds, and others were sent to Paris and San Francisco. DITL 2021 dataset case, after launching Brisbane node, 60% of queries from Australia to GRoot are sent to Brisbane node. Average RTT is 34.4 milliseconds. And these graphs show GRoot 2021 RTT CDF from Australia. RTTs from Australia to GRoot was over 120 milliseconds in 2020. 8% of queries, 25% of IP addresses were longer than 300 milliseconds. After launched Brisbane node, 28% of queries, 41% of IP addresses are answered within 30 milliseconds. And these are summaries. Anycast node name and query latencies can be measured from DITL dataset. GRoot Anycast seems to work well in Japan, North America, Europe, and Australia. GRoot Brisbane node provides short RTT for Australia. IP Anycast effectiveness of root servers may be analyzed in this method. This method may find the underserved area of root servers. And that's all.
We have nothing on the chat at the moment, and I do have actually one myself. Because, I was busy trying to follow to make sure there were no questions, so perhaps wasn't paying enough attention. Can you just go over again, please, how you're actually measuring the RTT? Are you, for example, looking at the time difference between individual queries arriving?
This slide?
Okay. And you're satisfied that we're not seeing overlapping queries from the same source IP address, making the queries appear closer together than they should be?
The difference, I ignored longer than 1 second delay because, for example, SYN-ACK dropped, then server resends next SYN-ACK packet after 1 second.
Okay. Thank you. We actually do have some more questions now. Yeah. Maybe let's take these questions actually just on the chat so that you can answer and read the English there. I appreciate that spoken English is difficult for you. Okay, thank you.
Thank you.
Okay, we'll pass back to you, Suzanne.
Thank you very much, Ray. Thank you very much, Fujiwara-san. 2 more quick things before we close. First of all, we didn't mention earlier, but there is a group in Mattermost, Women at OARC. You don't have to be of any particular persuasion to join, but it's there to encourage women to form connections and go ahead and participate, submit talks, do work that OARC would be interested in. Pallavi started it, I believe, and now that she's not the only woman in the PC, we can go ahead and encourage participation there. The only other thing I wanted to say was thank you very much to all of our speakers this afternoon and to the participants and the operations team. An enormous amount of information in a very short period of time. Very happy with how this has gone. I hope participants are also pleased, and I will turn it over to Keith for his closing.
Okay, we're nearly done. Just a few wrap-up remarks from me and the groundhog. Okay, so OARC 37, we only did 1 day today because of logistic constraints together with the usual pandemic stuff. So we'll do 2 more workshops this year. We'll make them 2-day ones. But I think we packed a very decent amount of content in. My slides? These ones, yeah. So social events. Unfortunately, we do not have a metaverse yet. So there are 2 social events. There is the spatial chat social event for the people who are participating online. We had 136 remote registrations. So that's, again, very good participation. You've probably used Spatial Chat before. There's the link. You should have received a password in the email that we sent out, or see that on the rolling slides. And it lets you move your little avatar around, and you can have conversations with people. For those of us who have already filled ourselves with cake and other stuff, there will be beer in the hotel. It says a rye bar in this slide, but actually there's an area off the main bar on the ground floor where we can gather for an hour or two. So next workshops. Throughout the last 2 years, the guiding principle is we want everybody to be able to participate safely. All events in 2021 were fully online. We will continue with hybrid events and try and provide the best equity that we can for those who are able and willing to travel and those who are not and are able to be in person. And we'll stick with that for as long as it takes. In general, your feedback is welcome on meeting format, duration, frequency, safety. So we have a couple of surveys for you to fill in as far as that's concerned. We also did some short OARC online workshops at various points over the past 2 years. We may do 1 or 2 of these, and also there are some ad hoc meetings of members as well. So our original plan for the spring 2022 workshop was to collocate with the ICANN IDS event, which also collocates with a number of ICANN events, which are not main ICANN meetings. They have unfortunately deferred that as an in-person meeting until the autumn or the fall of 2022. So we're looking at a number of options. Not all of these have been confirmed with the organizations that we might collocate with. We're still at the data gathering point at this time. But I suspect that anything in late April is probably going to be too soon. But there's an option to collocate with the RIPE meeting, and so that should be RIPE 84 in Berlin in mid-May, or we could go back with NANOG in June, or we could do a standalone meeting somewhere that's logistically straightforward for us, like Chicago or Toronto or Indianapolis or somewhere in the Great Lakes region of the US, North America. Or we could go with the IETF meeting in Philadelphia. We don't usually collocate with IETF, but there are reasons why that could work quite well, although it is a little bit later than we normally do it. Or, you know, if we're forced to, or if our members and attendees prefer, we could always go to an online-only meeting. So you'll see I've done yet another Mattermost poll. So it would be helpful if you're in the Mattermost chat to give us some feedback on that. There's also a survey question. I think another thing that we're quite interested in is just to understand, you know, we have 140 people registered, but we've only got 10 people in the room here. Just to understand what the reasons for that were and make sure that we're being responsive to that in terms of either helping people to plan or accommodating what their safety concerns are. The plan all along has been to collocate the fall OARC 39 meeting with RIPE 85 and Center Tech, which will be in Europe in October. So we're going to continue with that plan. So that's also something to bear in mind when we're looking at other options. It comes to the point where we get to thank everybody for everything that they've done. You know, these workshops don't just evaporate out of thin air. A lot of people do a lot of work. First of all, I would like to thank all the OARC members and supporters and sponsors and patrons whose support throughout the past 2 years has been absolutely solid. You know, the organization is in good shape, and without that would not be possible. The program committee, in particular, Willem and Suzanne for being our session chairs today. And I think they did it very smoothly considering that they were remote and not all the meeting was. Ray for being our Q&A monitor. Maurizio and Ulrich for supporting the social media feed of the event. My wife, Michaela, for volunteering to help out on the registration desk because some of the team members weren't able to travel. The team members who were not able to travel, Matt and Jerry and Steve, although they're not physically here, they've been doing all kinds of support activities behind the scenes. And you will find them as your hosts on the spatial chat and the social event this evening. Pallavi as our session chair, as the program committee chair, which she's just started doing for this year, and also Manu for help for backing her up on that, and also for running the Women at OARC group that's been mentioned. And a special thank you to all of our in-person attendees. it's a small audience, but one of the reasons that we went ahead with this is that we wanted to get some practice at running a hybrid meeting. And also thanks to everybody at the team at Clarity who have been awesome in terms of making all that work and being flexible and working with our way of doing things. So I think that, oh, and finally, also to Nanog, Edward and his team for working with us and cooperating on the co-location of the meeting. So we're still open for online and hybrid events via sponsorship. So please talk to Dinesh if you're interested in sponsoring the next one or any of our other meetings. And I think I thanked everybody, but I may have missed somebody. But yeah, that's a wrap. Again, please complete the survey for feedback and the Mattermost poll for the next location. And we will see you all in a few months' time and stay safe in the meantime. Thank you.